A supermassive black hole has been discovered on the move, traveling far beyond the galaxy where it once resided, dragging along a staggering trail of young stars that stretches over 200,000 light-years. This discovery, made possible by the Hubble Space Telescope, reveals an incredibly rare phenomenon in the universe, one that has captivated researchers studying galaxies and star formation. The black hole's journey is marked by a straight line of young blue stars that formed in its wake, providing a rare glimpse into the processes that occur when such an enormous object travels through space. Typically, black holes are situated at the center of galaxies. The discovery of one on the move at this scale is unexpected and has raised several important questions. The visible trail of stars is a direct indicator of the black hole's path and its interaction with the interstellar medium. Scientists believe that this black hole was likely ejected from its galaxy after a gravitational interaction with two other black holes during a galaxy merger. When three massive black holes collide, one can be ejected at extremely high velocities due to gravitational instabilities. This scenario, while predicted by theoretical models, is incredibly rare to observe. In this case, the black hole's velocity was so high it could escape the galaxy's gravitational pull entirely. The event offers solid proof of the extreme consequences that galactic mergers can have. As the black hole moves, it passes through gas clouds in the interstellar medium, compressing them as it goes. This compression generates shock waves and disturbances that trigger the formation of new stars along its path. These stars are young, blue, and linearly distributed, a configuration unlike the irregular or dispersed star-forming regions typically observed. This alignment strongly suggests that the black hole's movement directly influenced the birth of these stars. The phenomenon of star formation induced by a black hole is rarely observed, making this discovery particularly significant. The black hole involved is estimated to be about 20 million times more massive than the Sun, placing it firmly in the supermassive category. It is traveling at an astonishing 1,600 kilometers per second, fast enough to travel from Earth to the Moon in under 5 minutes. The sheer energy required to expel such an object is on par with the release of multiple supernovae occurring at once. This discovery has broader implications for our understanding of galactic structures. Or, without its central black hole, a galaxy may evolve differently. How these changes manifest is still being explored through simulations and theoretical models. This particular event provides a rare opportunity to observe and test these ideas in a real-world context. The presence of a moving black hole also raises new questions about the existence of wandering black holes. Many of these objects may exist outside the boundaries of galaxies, invisible to us without an accretion disk to shine light on their presence. However, when these black holes pass through gas-rich regions, their presence can be inferred from the stars they create or even from gravitational wave emissions. This suggests that wandering black holes may be more common than previously thought, with estimates suggesting there could be hundreds of millions scattered throughout the universe. Detecting such black holes will require new observational techniques. The trail of stars left by the black hole also offers an invaluable opportunity to study how gravitational shocks can collapse gas clouds and trigger star formation. Unlike traditional models that focus on local gravity, the external pressure exerted by the black hole seems to be enough to cause the gas clouds to collapse and form stars. This new perspective can complement and expand existing theories of star formation. Additionally, this discovery helps to explain linear structures in other parts of the universe, where the gravitational influence of massive objects may play a key role in shaping star formation. This breakthrough was made possible by the incredible sensitivity and resolution of the Hubble Space Telescope, which allowed astronomers to detect faint structures in distant regions of the sky. Without space-based observatories, such detailed observations would be impossible due to interference from Earth's atmosphere. The integration of observational data with theoretical models is essential for advancing our understanding of the universe. Discoveries like this provide the necessary real-world evidence to validate predictions made by decades of simulations on galaxy mergers. Although scientists had predicted such ejections, only recently have they found actual evidence to confirm these theories. This concrete example allows astronomers to fine-tune existing models and refine our understanding of galactic dynamics. The significance of this discovery goes beyond just satisfying curiosity. It has profound implications for how we view the distribution of black holes across the universe. If black hole ejections like this one are more common than we thought, it could mean that the centers of galaxies are less stable than previously assumed. The absence of a central black hole would alter the gravitational forces within the galaxy, affecting the movement of stars and gas and potentially altering the shape and evolution of the entire galaxy. This new insight challenges the long-held assumption that supermassive black holes must remain at the centers of galaxies. It opens up new avenues for investigating objects traveling alone through intergalactic space. The trail of stars left by the black hole allows astronomers to calculate its trajectory, speed, and the time since its ejection, providing crucial data for understanding how such a massive object was expelled from its galaxy. The alignment of the stars along the black hole's path, along with their similar age and spectra, allows scientists to estimate when the event took place and where it occurred. This data strengthens existing models of black hole interactions in multiple systems and provides critical parameters for validating simulations of galaxy mergers. The linear arrangement of the stars acts as a natural record of the gravitational disturbances caused by the black hole's movement, offering essential clues for understanding how extreme masses influence star formation in low-density environments. This discovery is just the latest in a series of breakthroughs that are reshaping our understanding of the cosmos. It underscores how much more there is to learn about the universe's most mysterious and powerful objects. In the depths of a neutron star, there exists a remarkable structure known as nuclear pasta, a form of matter that plays a critical role in the star's stability. This unique material forms in an intermediate zone between the star's solid crust and its deep liquid core, where the balance between compression and organization creates a strong yet complex structure. Research has shown that nuclear pasta is up to 10 billion times stronger than steel, with its strength deriving from the way protons and neutrons bond together, forming patterns that are incredibly tough to break. This extraordinary layer provides rigidity to the star's crust, enabling it to endure distortions that in other contexts would cause it to fracture. Even the slightest changes in the crust can generate gravitational waves, which scientists study to understand when and how a star might emit these signals. This connection between the star's internal structure and the external phenomena observed is a key area of focus in astrophysical research today. Nuclear pasta forms in a region where atoms can no longer retain their usual shape, but haven't collapsed into chaos either. As the depth increases within the star, the atomic nuclei flatten, stretch, and begin to fuse into intricate geometric networks. These networks form shapes such as sheets, tubes, and spheres, which significantly influence how heat and waves move through the star. The pasta's unique structure helps maintain the star's stability, even when it is rapidly spinning or exposed to intense magnetic fields. Without this structure, the star's internal balance would be altered, leading to different physical behaviors. The rigidity of nuclear pasta also helps explain a phenomenon known as glitches, which are sudden jolts in the rotation of pulsars, neutron stars that spin at incredibly high speeds. These glitches occur when tension builds up in the crust and is suddenly released. Nuclear pasta gives the star's crust the strength to hold and release energy, and by observing these glitches, scientists can infer the star's internal processes, testing theories about its density and structure. Another crucial function of nuclear pasta is its effect on the cooling of neutron stars. Neutrinoles, which are particles that carry away energy, interact with nuclear pasta at a different rate than they would in normal materials. This altered interaction changes how a star loses heat over time. By comparing temperature variations across different neutron stars and matching them with simulations, scientists can test the accuracy of models that account for the presence of nuclear pasta. Small discrepancies in temperature curves can help refine the physical parameters used in these models, improving our understanding of how neutron stars evolve. Nuclear pasta also influences the star's magnetic fields, particularly in magnetars, neutron stars with extremely strong magnetic fields. The crust's rigid structure, reinforced by the pasta, prevents the magnetic field lines from easily shifting, which can cause energy to build up and eventually be released explosively in gamma-ray bursts. These bursts have been observed in several instances and are believed to be linked to instability in the star's crust. Therefore, the strength of nuclear pasta directly connects to some of the most violent and well-documented events in astrophysics. In addition to its role in individual stars, nuclear pasta also plays a part in neutron star mergers, which have been detected on Earth as gravitational waves. When two neutron stars collide, part of the crust is destroyed, and the nuclear pasta may be released or heated, altering the signals detected in light, gamma rays, and gravitational waves. Comparing these observations with theoretical predictions helps scientists understand the role of nuclear pasta in these extreme events. While such mergers are rare, they provide a unique opportunity to study matter under extreme conditions. The amount of nuclear pasta in a neutron star varies based on the star's mass and age. In some stars, it forms a wide region, while in others, it's much thinner. This variation is crucial for understanding the properties of different pulsars and allows scientists to compare and identify repeating patterns across various neutron stars. As more data is collected, researchers can narrow down the density and pressure ranges where nuclear pasta is likely to form, further refining our knowledge of this enigmatic material. Since it is impossible to recreate nuclear pasta in a laboratory on Earth, scientists rely on supercomputer simulations to model how matter behaves under these conditions. They use equations from nuclear physics to predict the behavior of matter in neutron stars, and compare these predictions with data collected from telescopes and detectors. If the simulated results consistently match the observed behavior, it reinforces the theory of nuclear pasta. Even without direct observation, the theory remains solid as long as it explains the data accurately. One of the most critical roles nuclear pasta plays is determining how much gravity a neutron star can withstand. If the crust is highly resistant, the star can support more mass before collapsing into a black hole. Conversely, if the crust is less resistant, the collapse occurs at a lower mass. This characteristic impacts the observed mass distribution of compact objects and is essential for defining the boundary between stars and black holes. As a result, nuclear pasta is included in calculations related to the evolution of binary systems and collision events. Despite being an exotic form of matter, nuclear pasta has observable effects on a variety of astrophysical phenomena. From changes in pulsar rotation to gamma-ray explosions, its presence can be detected through its influence on the star's behavior. This highlights how, even without directly seeing nuclear pasta, scientists can study it through its observable effects. This is a prime example of how science works. What cannot be directly observed can often be deduced from reliable data. In the case of nuclear pasta, the evidence continues to support its existence, making it a central component in understanding the interiors of the densest stars in the universe. Furthermore, nuclear pasta offers a unique opportunity to test the limits of physics in extreme environments. It challenges our understanding of how known laws of physics hold up under conditions vastly different from those on Earth. So far, the theory of nuclear pasta has remained consistent with observations, further solidifying its importance in the broader framework of nuclear physics. By studying nuclear pasta, scientists gain insight into how matter behaves under some of the most extreme conditions in the cosmos, ultimately building a more complete picture of the universe's most mysterious and powerful objects. As space dust enters Earth's atmosphere, it slows down due to friction and eventually falls to the ground like tiny particles. This process helps preserve the dust's structure, making it an invaluable source of information about the early solar system. Unlike meteorites, which are much rarer, these microscopic grains arrive in much greater quantities. Most of this dust comes from comets, which break apart as they approach the sun. Solar radiation heats up the comets, causing them to release gases and solid particles. Over thousands of years, these particles spread along orbits around the sun, and when Earth crosses these paths, some of the material enters our atmosphere. This is the same process that causes meteor showers, but the finer dust particles remain unnoticed, falling continuously. Aside from comets, asteroid collisions also generate debris, some of which eventually intersects Earth's orbit. Most of the space dust that lands on Earth is found in isolated regions, far from human interference. To distinguish these space particles from ordinary dust, scientists employ specific techniques, such as filtering out particles from melted ice, using microscopes for close examination, and analyzing their chemical composition. These particles often have spherical shapes and are rich in iron and nickel, distinguishing them from common terrestrial dust. Studying these particles offers insight into the history of collisions and the formation of smaller bodies within the solar system. Micrometeorites have been found to contain complex organic compounds, suggesting that some of the building blocks of life may have been transported to Earth via space dust. While these compounds don't indicate life themselves, they include carbon-based molecules that can participate in biological reactions. The presence of amino acids and other simple compounds in larger meteorites has already been confirmed, and micrometeorites could have been carrying these organic materials continuously over billions of years. This ongoing transfer supports theories that life's building blocks may have originated from sources beyond Earth. These micrometeorites also carry valuable information about their thermal history. As they travel through the atmosphere, many particles experience partial melting, showing signs of surface heating. This allows scientists to study how atmospheric friction affects particles of varying sizes and speeds, and helps refine models of atmospheric entry. These models are useful not only for Earth, but also for other planets like Mars, as well as moons with atmospheres. Some micrometeorites even contain rare isotopes, which can serve as markers to identify their origins. The accumulation of space dust has practical implications, especially in Earth orbit. Satellites and telescopes in space must be protected from the impact of these high-speed particles. Even tiny grains of dust can damage sensitive equipment. For example, the International Space Station has outer layers designed to absorb the impact of micrometeorites. While the risk of space dust on Earth is minimal, in space it plays a crucial role in the design of spacecraft. Thus, space dust influences both scientific research and technological development. Beyond their constant accumulation, space dust particles build up in large volumes over thousands of years. Estimates suggest that trillions of tons of dust have accumulated on Earth since its formation. In polar regions, this dust becomes trapped in ice layers, providing scientists with a way to track deposition rates from different geological periods. By studying these layers, researchers can learn about variations in cometary activity and asteroid collisions, offering insight into the dynamic history of the solar system. This dust record complements other data sources, like preserved craters and meteorites, and serves as an indirect indicator of solar system events. In the ocean, cosmic dust settles gradually on the seafloor, mixing with marine sediments. In areas with low terrestrial sedimentation, such as abyssal plains, this dust is easier to identify. Scientific expeditions collect samples from the ocean floor, using techniques like mass spectrometry and imaging to detect metallic traces characteristic of space dust. By comparing dust compositions from various regions of the planet, scientists can track seasonal variations and identify extraordinary events that may have led to an increased influx of material. While space dust is invisible to the naked eye, it can still be collected in urban areas using strict separation methods. For instance, micrometeorites may accumulate on rooftops, mixed with pollutants and local dust. With patience and proper lab techniques, these particles can be identified as visitors from space. Some educational programs encourage people to search for micrometeorites as a way to engage with astronomy and geology. Though the success rate is low, it's a practical way to connect everyday life with cosmic processes, showing that we are unknowingly in direct contact with space. The amount of space dust Earth receives generally remains consistent over time, but it can fluctuate due to events like the fragmentation of comets or major asteroid collisions. Detecting these variations in geological records helps scientists understand past events that may have left no other trace. This growing field of astrogeology holds the potential to reveal periods of intense solar system activity. These discoveries highlight the importance of studying materials that may initially seem insignificant, but hold a wealth of cosmic history. By combining chemical, isotopic, and morphological analyses, scientists can trace the probable origin of many particles. Some come from the asteroid belt, while others originate from long-period comets. This research enhances our understanding of the diversity of smaller bodies in the solar system and provides a way to compare Earth-bound materials with those collected by space missions, such as asteroid samples returned by probes. These direct comparisons help validate models of the solar system's chemical evolution. Micrometeorites thus act as a bridge between the cosmos and the tangible objects scientists study on Earth. In a related story, Eugene Shoemaker, the only person whose ashes were sent to the Moon, played a pivotal role in the field of astrogeology. A geologist and astronomer, Shoemaker helped establish that many craters on Earth and the Moon were formed by asteroid impacts, not volcanic activity as previously thought. He also trained Apollo astronauts in lunar geology, making significant contributions to our understanding of the Moon's surface. In collaboration with his wife Carolyn and astronomer David Livy, Shoemaker co-discovered Comet Shoemaker-Levy 9, which famously collided with Jupiter in 1994. This was the first time humanity witnessed a large-scale impact on another planet, further emphasizing the importance of Shoemaker's work. Though Shoemaker's medical condition prevented him from becoming an astronaut, his influence remained significant throughout NASA's space missions in the 1960s and 1970s. He led research on terrestrial craters like Meteor Crater in Arizona, which served as analogues for lunar geology. Shoemaker's work contributed to mapping the Moon's surface based on Apollo mission samples. After his death in 1997, a portion of his ashes was sent to the Moon aboard the Lunar Prospector spacecraft, where it remained a symbolic tribute to his lifetime of contributions to space science. The impact occurred near the Moon's south pole, a region of great interest due to the potential presence of ice deposits. It was at this exact moment that Eugene Shoemaker's ashes made contact with the lunar surface, symbolizing the conclusion of a mission that combined scientific exploration with a personal tribute. From a scientific perspective, sending Shoemaker's ashes had no impact on the mission's objectives. The amount of material was so small that it was integrated symbolically into the spacecraft's structure. NASA approved this gesture as a fitting recognition of Shoemaker's contributions to planetary science. The decision to have the probe crash into the Moon was already part of the planned conclusion of the mission, and the inclusion of this tribute was seen as a respectful acknowledgement of Shoemaker's important work in lunar geology. This blend of science and homage is rare, but it did not interfere with the technical goals of the mission. The capsule containing Shoemaker's ashes was designed to withstand the crash, ensuring it remained intact. However, since the exact impact site is not easily identifiable, Shoemaker's remains have effectively become part of the Moon's regolith. This means that, in a symbolic sense, he is now permanently part of the Moon's surface. While the exact location of the impact is not marked or accessible, the general region where the spacecraft landed is considered Shoemaker's symbolic resting place. Unlike other tributes, this one stands out for involving the actual remains of a person being sent to another celestial body. Shoemaker's case sets a unique precedent in the history of space missions involving human remains. While private companies have sent ashes into Earth's orbit or beyond, his remains were sent specifically to the surface of the Moon, a move that remains unparalleled due to technical challenges, costs, and logistical issues. This type of tribute is unlikely to be replicated on a large scale. Shoemaker's example remains a singular and poignant tribute to his legacy as a pioneer in planetary exploration. Titan, Saturn's largest moon, is a fascinating world, where the only known surface lakes and seas are made of liquid methane and ethane, not water. These liquid reservoirs exist because Titan's surface temperature hovers around -79 degrees Celsius, allowing these hydrocarbons to remain in liquid form. This creates a methane-based hydrological cycle, similar to Earth's water cycle, but instead of water it involves methane. Evaporation, condensation, and precipitation all occur in Titan's frigid atmosphere. This process, although powered by solar energy, is much weaker due to Titan's distance from the Sun. Despite this, Titan's atmospheric system is surprisingly dynamic and complex. The first solid confirmations of this methane cycle were made by the Cassini-Huygens mission, which orbited Saturn from 2004 to 2017. In 2005, the Huygens probe successfully landed on Titan and recorded evidence of damp terrain covered in organic materials, providing crucial insights into its surface and atmosphere. Cassini's radar and spectrometers also mapped extensive liquid methane bodies near Titan's poles, such as Kraken Mare and Ligeia Mare, which span vast areas and reach depths of over 100 meters in some places. These liquid seas are primarily composed of methane with traces of ethane and nitrogen. Much like lakes on Earth, these liquid bodies form in topographic depressions, revealing a landscape shaped by the processes of erosion and accumulation. Titan's atmosphere is mostly nitrogen, with about 5% methane and traces of other organic compounds. Methane plays a crucial role on Titan, acting much like water does on Earth, forming clouds, fueling rainfall, and feeding the lakes and seas on the surface. Observations have revealed moving clouds, suggesting active rainfall events. Some areas show signs of erosion, with carved channels and smooth surfaces, typical of regions shaped by recent liquid flows, proving that Titan's surface is actively evolving, despite the extremely cold environment. Methane rain on Titan isn't constant, but occurs in seasonal patterns tied to the Moon's axial tilt and its orbit around Saturn. Each season lasts about 7 Earth years, and because of Titan's tilted axis, the climate varies significantly between hemispheres. For example, during the northern polar summer, increased atmospheric activity is seen, with more cloud formation and rainfall events. These seasonal rains contribute to the filling and draining of lakes and the formation of new river channels. Interestingly, Titan's lakes are not evenly distributed. Most are concentrated in the northern hemisphere, a phenomenon that scientists are still working to understand. Titan's methane cycle offers a natural laboratory for studying climate systems in extreme environments. The behavior of its lakes, clouds, and rainfall gives scientists the opportunity to test atmospheric models under conditions vastly different from those on Earth. Titan's low gravity and dense atmosphere create a unique setting for studying evaporation and precipitation on a planetary scale, revealing new insights into how frozen ground and liquid hydrocarbons interact to form novel types of erosion. These methane lakes also influence Titan's energy balance. They absorb and reflect sunlight differently than dry terrain, which impacts local climate patterns. Furthermore, the evaporation of methane contributes to the formation of fog and stratospheric clouds. These organic aerosols scatter sunlight, giving Titan its distinct albedo. Studying these processes helps scientists understand planetary atmospheric behaviors, including the formation of haze layers on primitive planets. Titan's complex atmosphere also sheds light on how the phases of matter, solid, liquid, and gas, interact in diverse planetary contexts. The organic chemistry occurring on Titan is especially intriguing. Ultraviolet radiation from the sun interacts with methane in Titan's upper atmosphere, triggering a cascade of complex chemical reactions. These reactions produce larger hydrocarbons and organic compounds like acetylene and ethane, which then settle on Titan's surface as solid aerosols or dissolve into its lakes, contributing to the Moon's unique chemical makeup. Though the environment on Titan is too cold to support life as we know it, it offers valuable clues about the early stages of prebiotic chemistry. Titan, in this sense, serves as a key reference for studying chemistry in extreme conditions, helping us understand the potential for life in environments vastly different from Earth. Interest in Titan has led to plans for future missions, such as NASA's Dragonfly, scheduled for launch in the next decade. Dragonfly will use a nuclear-powered drone to explore Titan's surface, studying its composition, atmospheric dynamics, and chemical processes. Titan's low gravity and thick atmosphere make it particularly well suited for aerial exploration, and the Dragonfly mission promises to deliver unprecedented data on the Moon's liquid cycles, geology, and surface chemistry. It will be the first mobile mission to Titan, enabling scientists to explore its surface in ways never before possible. The presence of liquid hydrocarbons on Titan, though too cold for life as we know it, raises intriguing questions for astrobiology. Could methane and ethane serve as solvents for life forms that are radically different from those on Earth? While no evidence of life has been found on Titan to date, the study of environments with active liquid processes is essential for understanding the wide range of potentially habitable conditions that could exist on other worlds. Space exploration is often filled with surprising facts that help us put things into perspective. For example, the entire solar system could fit within the distance between the Earth and the Moon. The average gap between our planet and its satellite is about 384,400 kilometers, which seems like a long way, but it's surprising to realize that this distance could accommodate the diameters of all the planets in the solar system, lined up side by side. If we add up the diameters of Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, it comes to roughly 380,000 kilometers. While this excludes the vast empty space between the planets, it's still a striking reminder of how much empty space there is even within our own solar system. The Moon may look close to Earth, especially during its full phases, but in reality it's about 30 times the size of Earth. This simple comparison shifts how we think about the scale of the planets and the distances that separate them. Of course, this only compares their physical sizes, not their orbits, which stretch out far beyond what we can see with the naked eye. The orbits of planets span billions of kilometers, creating vast, empty stretches of space between each one. When we focus purely on their physical sizes, the distance between Earth and the Moon takes on a new meaning. It highlights just how small the planets are compared to the immense space separating them. This perspective is essential for understanding human space exploration. Although we've only traveled to the Moon, that journey alone covers a distance wide enough to fit the entire set of planets in the solar system. It emphasizes the scale of nearby space, and that's often difficult to grasp. Educational models and visualizations are incredibly helpful in illustrating this concept. These models show planets lined up within the Earth-Moon distance, and when you see this comparison, you start to truly grasp the immensity of the distances between celestial bodies. It also helps correct a common misconception about the solar system's scale. Most models tend to exaggerate the size of planets and distances to fit on screens or paper. These real-scale comparisons restore the actual proportions and deepen our understanding of orbital mechanics. In astronomy, the Earth-Moon distance is a fundamental reference unit, especially when measuring the distances of near-Earth objects. For example, asteroids that come within a lunar distance are considered to be making a close approach to Earth. Using this measurement makes it easier for scientists to communicate potential risks. The fact that all the planets can line up within this space puts into context how vast the distances between objects in our solar system are. It reinforces the idea that space is defined more by emptiness than by the objects themselves. This distance is also crucial in understanding gravitational effects. The Earth-Moon distance is where Earth's gravity still dominates, but the Moon's gravitational influence starts to take hold. This delicate balance of gravitational forces plays a huge role in things like ocean tides here on Earth, which are shaped by the Moon's position. It's a perfect example of how distance and mass interact in orbital dynamics. And this balance is essential for the stability of the Earth-Moon system. Knowing how these forces work is key for planning lunar missions and satellite launches. The Earth-Moon distance has also been an important proving ground for many space technologies. Radar measurements to the Moon were some of the first long-range space tests, and today, laser ranging is used to measure the Earth-Moon distance with incredible accuracy. By bouncing laser beams off retroreflectors left by the Apollo astronauts, scientists can measure the distance to the Moon with millimeter precision. This data not only helps us understand the size of the gap between Earth and the Moon, but also reveals that the Moon is slowly drifting away from Earth at a rate of about 3.8 centimeters per year. These measurements underscore just how vast the empty space between Earth and the Moon truly is. Although the planets in our solar system are massive, their actual diameters are much smaller than the distances that separate them. For example, Jupiter, the largest planet in the solar system, has a diameter of about 143,000 kilometers, which is still only a third of the Earth-Moon distance. Even when all the planets are placed side by side, they don't fill the entire gap between Earth and the Moon. This realization is helpful for astronomers, as it helps them model other planetary systems and understand how planets might be arranged in exoplanetary systems. This insight often surprises people, even those with a strong interest in astronomy. That's because our human intuition tends to underestimate both the size of objects in space and the vastness of the distances between them. Tools that highlight these true-scale comparisons can significantly improve our understanding of the universe. They help us realize just how much space is out there, space that we've only just begun to explore. While we've sent probes across the solar system, human presence has only reached the first step, the Moon. This sense of scale is fundamental when planning future missions to Mars or beyond. To get to Mars, we'd need to increase the distance traveled by many times over, and the Earth-Moon distance provides a helpful frame of reference to understand how much farther we'll need to go. Beyond the Earth-Moon system, one of the most exciting places to explore is Europa, one of Jupiter's moons. Beneath its thick ice crust, scientists believe there's a global ocean of liquid water, and it could potentially harbour life. The ice on Europa is estimated to be about 15 to 25 kilometers thick, and the ocean beneath could be as deep as 60 to 150 kilometers. This vast liquid ocean might contain more water than all of Earth's oceans combined. The ocean is likely in contact with a rocky mantle, which could provide the chemical ingredients needed to support life. Evidence for this ocean comes from data collected by the Galileo spacecraft in the 1990s, which found a conductive layer consistent with salt water. More recently, observations from the Hubble Space Telescope confirmed that plumes of water vapor are erupting from Europa's surface. Europa's surface is geologically active, with fractures, ridges, and terrain that show signs of movement. These features suggest that there is an ongoing exchange of materials between the ocean below and the surface. This dynamic activity could provide the necessary nutrients and energy for life. Some areas of Europa, known as chaos terrain, have been formed by subsurface heating and material upwelling which later refroze. These processes could bring chemical compounds from the ocean to the surface, where they could be studied by spacecraft. The detection of hydrated salts and sulfuric acid further suggests that Europa has a geologically active system. The presence of a liquid ocean is a strong indicator that Europa could be a habitable environment, but it's not enough on its own. For life to exist, there must be a source of energy. On Earth, life thrives around hydrothermal vents on the ocean floor, where heat and chemical energy support microbial ecosystems independent of sunlight. Europa's ocean could have similar hydrothermal activity at its seafloor, fueled by tidal forces from Jupiter. These vents could create an environment capable of supporting life, much like the deep-sea vents on Earth. Europa's surface temperature is extremely cold, averaging around -160 degrees Celsius, and its lack of a significant atmosphere makes the surface uninhabitable. However, any biological material near the surface would be preserved by these harsh conditions. The water vapor plumes that have been observed erupting from Europa's surface might provide a rare opportunity to study Europa's internal ocean without drilling through kilometers of ice. NASA's upcoming Europa Clipper mission, scheduled for launch in the late 2020s, will perform detailed flybys of Europa, studying its ice shell, subsurface ocean, and surface composition in search of signs of life. This mission represents a major leap forward in our understanding of Europa's potential to host life. In addition, the European Space Agency's Jupiter Icy Moons Explorer mission, or JUICE, will also study Europa along with Ganymede and Callisto. JUICE will conduct multiple flybys of Europa, providing complementary data to the Europa Clipper mission. Upcoming missions are designed to give us a complete understanding of Jupiter's icy moons, with Europa being one of the primary targets. The evidence for a liquid ocean beneath Europa's thick ice and the presence of geological activity make it an exciting place for further investigation. These missions will combine data from both orbital observations and surface measurements to test various hypotheses about the moon's chemistry and internal dynamics. Each new piece of data will help reduce uncertainties and improve our models of the moon's environment. Europa's surface is bombarded by radiation from Jupiter's powerful magnetic field, creating a layer of reactive compounds on the ice. If these compounds are transported into the subsurface ocean, they could provide chemical energy for potential life forms. A crucial part of these missions will be to study how the surface chemistry connects to the ocean below, as this interaction plays a significant role in determining the availability of nutrients and the moon's potential for habitability. Understanding this delicate balance between radiation processing on the surface and internal cycling is key to assessing Europa's bioenergetic potential. Europa's ability to support life is important not only for astrobiology, but also for comparative planetology. This studying how oceans of liquid water evolve beneath thick layers of ice can improve our understanding of similar environments found on exoplanets and other moons. Europa offers a nearby accessible example to help test theories about the limits of life and chemical self-organization. Discoveries made on Europa could redefine our understanding of the conditions under which life can arise and persist. This also helps frame the broader search for habitable environments beyond Earth. Beyond the search for life, Europa's ocean and surface composition are important to planetary science. Its combination of water, energy sources, and geological activity makes it one of the most compelling targets in the solar system for exploration. The upcoming missions will reveal more about the nature of Europa's ocean, how it interacts with the icy surface, and whether there's exchange between the two. As the spacecraft gather high-resolution data, our understanding of this distant world will evolve rapidly. Europa remains one of the most scientifically intriguing places beyond Earth, and its exploration promises to yield important insights into the possibility of life elsewhere in our solar system. Another major aspect of our solar system is the Sun, which contains 99.8% of the total mass of the entire system. The Sun's immense mass explains its dominant gravitational influence, which binds all the planets, asteroids, and comets in the solar system. The remaining 0.2% of mass is spread among the planets, moons, dwarf planets, and smaller objects. Even Jupiter, the largest planet, contains less than 0.1% of the solar system's total mass. This concentration of mass in the Sun means it exerts immense gravitational force over all the bodies in the system. The Sun's mass is around 1.989 × 10 circumflex 30 kilograms, a figure that is difficult to grasp in practical terms. The Sun is primarily made up of hydrogen, about 74%, and helium, about 24%, with small amounts of heavier elements. At its core, nuclear fusion converts hydrogen into helium, releasing vast amounts of energy. This energy not only sustains the Sun against gravitational collapse, but also provides the light and heat that make life on Earth possible. Without this mass, fusion wouldn't occur, and the solar system as we know it would be entirely different. The Sun's gravity is responsible for the orbits of all planets and other bodies in the system. Its mass warps space-time, creating the elliptical orbits of the planets as described by Einstein's theory of general relativity. Any significant loss of mass from the Sun would disrupt the balance of the solar system's orbits. For instance, if the Sun lost even a small fraction of its mass, Earth's orbit would shift outward. This centrality of mass makes the Sun the dynamic anchor of the entire system. Additionally, the Sun's mass influences the barycenter, the center of mass around which both the Sun and the planets orbit. Although the barycenter usually lies within the Sun's volume, it shifts slightly depending on the positions and masses of the planets. Jupiter, being the largest planet, causes the greatest displacement, which, although subtle, is measurable and used in precision tracking of solar system dynamics. This understanding of how the barycenter shifts helps improve our models for spacecraft navigation and planetary predictions. It also highlights the interconnectedness of all bodies in the solar system under the Sun's gravitational influence. The Sun's dominance also ensures the long-term stability of the solar system's orbits. Even distant objects like comets and dwarf planets are kept in place by the Sun's gravitational pull over millions of years. The Oort cloud and Kuiper belt, which are light years away, are still gravitationally bound to the Sun, with objects in these regions following slow, elongated orbits. These areas contain remnants from the early solar system, preserved in cold isolation. The fact that the Sun retains control over such vast regions further emphasizes the incredible reach of its gravity. Though the Sun does lose mass, it happens at an extremely slow rate. The Sun loses about 4 million tons of mass per second due to fusion and solar wind. While this loss is significant on astronomical timescales, it's negligible for us in the short term. Over billions of years, however, the Sun's mass loss will begin to influence the orbits of the planets. As the Sun ages and enters the red giant phase, this mass loss will accelerate, causing the outer planets to gradually move outward. Understanding this gradual change helps scientists predict the distant future of the solar system. The Sun's mass also affects the orbital resonances within the solar system, particularly in the asteroid belt and among moons. These resonances occur when gravitational interactions lock objects into specific orbits. The Sun's gravity is the driving force behind these patterns, and without it, these stable configurations wouldn't persist. Resonances play a crucial role in maintaining order in areas that could otherwise be chaotic, helping scientists understand how planets and moons evolved from the early solar system's disk material. Historically, measuring the Sun's mass was key to understanding planetary motion. By observing Earth's orbit and applying Newton's law of gravitation, astronomers were able to calculate the Sun's mass indirectly. Later, spacecraft tracking and solar seismology refined this value, leading to highly accurate predictions of orbital movements. This precision is essential for mission planning, navigation, and testing gravitational theories with real-world data. Enceladus, one of Saturn's moons, has become another point of interest due to its active geysers. These plumes, which consist of water vapor, ice particles, salts, and organic compounds, erupt from fractures near its south pole. The Cassini spacecraft passed through these plumes several times and analyzed their composition, revealing that Enceladus harbors a subsurface ocean beneath its icy crust. The discovery of liquid water and complex molecules sparked immediate interest in the possibility of habitability. The plumes were first confirmed in 2005 when Cassini captured high-resolution images and detected increased concentrations of water vapor. Observations later revealed that material was being ejected from Enceladus at speeds fast enough to escape its gravitational pull. Some of these particles fall back onto the moon's surface, while others travel into space, contributing directly to the creation of Saturn's E-ring. This narrow, icy ring is constantly replenished by Enceladus, making it a unique link between a moon and a planetary ring in our solar system. It highlights the dynamic and often surprising interactions that can occur even with small icy moons. Cassini's instruments detected not only water and ice, but also salts such as sodium and potassium, along with organic compounds like methane and molecular hydrogen. These substances point to the possibility of hydrothermal activity occurring at the ocean's floor, where heated water might be interacting with rock. On Earth, similar environments support life through chemosynthesis, a process that doesn't rely on sunlight. The presence of molecular hydrogen is particularly intriguing, as it could serve as a chemical energy source for microbial life, similar to the conditions found in deep-sea hydrothermal vents on Earth, where life is believed to have originated. The temperature inside Enceladus is kept warm by tidal heating, a consequence of gravitational interactions with Saturn and its neighboring moons. As Enceladus follows its eccentric orbit around Saturn, the varying gravitational forces cause internal friction, generating heat. Despite the moon's frigid surface temperature of around -200 degrees Celsius, this heat keeps the subsurface ocean liquid. It also drives the periodic flexing of the ice shell, maintaining the iconic tiger stripe fractures on the surface. Without this internal heat, Enceladus would likely be geologically inactive, like many other small moons in the solar system. Cassini's close flybys revealed some unusual mass anomalies beneath Enceladus's south pole. These anomalies confirmed the presence of a large ocean beneath the moon's icy crust. Additional data from the spacecraft's magnetometer showed disruptions in Saturn's magnetic field near Enceladus, likely caused by the conductive nature of the ocean. These findings helped refine models of the ocean's depth and salinity, suggesting that it's in contact with a silicate core which could facilitate complex chemical exchanges. This makes Enceladus one of the few known places in the solar system where liquid water and geochemical conditions may support life. The surface of Enceladus, especially around the tiger stripes, is incredibly young and smooth, indicating recent resurfacing. Craters are scarce in these areas, suggesting that the surface is continually being renewed. This ongoing geological activity supports the idea that material from the subsurface ocean is reaching the surface and freezing. These frequent changes are significant for astrobiology, as they allow for the study of subsurface materials without the need for drilling. The plumes, which carry ocean samples into space, provide a direct way to analyze these materials with spacecraft. The constant exchange between Enceladus and Saturn's E-ring highlights the moon's active role in shaping its environment. Unlike moons that merely orbit passively, Enceladus actively contributes to the dynamics of space around it. The particles from its plumes form a torus of material that interacts with Saturn's magnetosphere, affecting its plasma environment and the evolution of the rings. This discovery challenges previous assumptions about the stability of planetary systems, and shows how even small celestial bodies can have a major impact on their larger planetary systems. NASA, along with other space agencies, has shown strong interest in sending a dedicated mission back to Enceladus. Future spacecraft could sample the plumes in even greater detail, searching for biosignatures and molecules tied to biological activity. Such missions wouldn't need to land or drill, making them more cost-effective and simpler to execute. The goal would be to detect organic molecules, isotopic ratios, and possibly cellular structures. Given the ease of accessing ocean material in the plumes, Enceladus presents a prime opportunity to search for life beyond Earth. The potential scientific rewards are immense. Although its size and distance from the Sun might suggest an inhospitable environment, Enceladus's internal processes create conditions that could support life. Unlike many icy moons with no geological activity, Enceladus maintains a dynamic interior and an open exchange with space. The consistent activity of the plumes over the years shows that this is not a fleeting phenomenon. Each eruption offers scientists valuable insights into the structure and contents of the subsurface ocean, reshaping our understanding of habitability in the outer solar system. Now, shifting focus to Io, one of Jupiter's moons, it is by far the most volcanically active body in our solar system. With more than 400 active volcanoes scattered across its surface, Io experiences eruptions that send plumes of gas and particles soaring up to 400 kilometers into the atmosphere. Observations from spacecraft like Voyager, Galileo, and Juno have revealed the immense scale of Io's volcanic activity, with eruptions covering vast areas in sulfur and silicate lava. This constant reshaping of its surface makes Io geologically unique. The source of Io's volcanic fury is tidal heating, caused by the gravitational forces exerted by Jupiter's massive gravity. As Io orbits Jupiter in an elliptical path, it is continually pulled and flexed. This tidal stretching generates immense friction inside the moon, producing heat. Unlike Earth, where internal heat comes mainly from radioactive decay, nearly all of Io's internal energy is generated through tidal forces. This heat powers volcanic eruptions and drives the moon's dynamic geology. Io's plumes, mostly composed of sulfur dioxide gas, sulfur particles, and volcanic dust, form large umbrella-shaped clouds that can stretch hundreds of kilometers in the atmosphere. The plume's height of up to 400 kilometers is made possible by the moon's low gravity and the high pressure of the erupting gas. These eruptions are short-lived, with features often disappearing within a matter of days or weeks. By tracking the activity of Io's volcanoes, scientists gain valuable insights into the movement of magma beneath the surface. Among Io's most powerful volcanoes is Loki Patera, which periodically experiences bursts of volcanic activity. Other volcanoes like Prometheus, Pele, and Tevashtar have distinct eruption patterns, some of which are continuous while others produce massive bursts. The varied eruption styles offer a rare look into the different volcanic processes at play, which are seldom seen together even on Earth's most active volcanoes. The surface of Io is rich in colorful deposits, primarily from volcanic activity. These sulfur compounds give the moon its distinctive yellow, red, and white regions, while dark basaltic lava flows cover other areas. Unlike icy moons, Io has little to no water, and its geology is driven mainly by rock and sulfur interactions. Its thin atmosphere, mostly sulfur dioxide, is temporary, collapsing at night and allowing volcanic gases to either escape into space or fall back as frost. Io's volcanic activity also affects Jupiter's magnetosphere. The particles ejected from the moon form a plasma torus, a ring of charged particles that orbits the planet. As Io moves through this region, it interacts with the plasma torus, influencing the planet's magnetosphere and producing auroras. The charged sulfur and oxygen particles contribute to the intense radiation environment surrounding Jupiter, giving scientists an opportunity to study the broader interactions between moons and their parent planet's magnetic fields. Amidst constant geological activity means that its surface is one of the youngest in the solar system. The rapid resurfacing, driven by volcanic activity, erases old impact craters and refreshes the terrain in just a few years. This high turnover makes it difficult to track specific surface features over time, requiring constant updates to surface maps. The young surface of Io is a living example of how planets and moons can be geologically reshaped on a planetary scale. In terms of temperature, Io's surface can reach temperatures exceeding 1,300 K during volcanic eruptions, indicating extreme conditions in its interior. Spectroscopic observations have confirmed the presence of silicate components and thermal hotspots, further revealing the moon's intense geologic activity. The heat generated by Io's eruptions far surpasses that of any other moon in the solar system, making it an excellent subject for studying early planetary conditions and high-temperature geological processes. Spacecraft like Juno continue to offer valuable data during their flybys of Io. The key challenge, however, lies in understanding the internal dynamics that drive such constant volcanic eruptions. Scientists combine tidal models with thermal and geological data to simulate mantle convection and crustal processes. These models are crucial for piecing together the moon's internal structure and understanding how magma moves within it. Each eruption offers new data points, helping to refine these simulations. Studying Io gives scientists a rare, real-time glimpse into volcanic activity under conditions vastly different from Earth's. The frequency and intensity of volcanic features on Io offer an excellent opportunity to test planetary geology models. In a way, Io serves as a natural laboratory for understanding how internal energy sources can shape a body's surface without solar input. Its active volcanism also adds complexity to the broader Jovian system. For planetary scientists, Io is both a challenge and a resource, providing insights into high-energy geophysical processes that can't be studied in such detail anywhere else. Switching gears, on August 5, 2013, the Curiosity rover marked its first year on Mars. To celebrate, the engineers at NASA's Jet Propulsion Laboratory programmed the rover to sing Happy Birthday to itself. This wasn't a festive gesture, but rather a technical demonstration of the rover's capabilities. Using the Sample Analysis at Mars, SAM instrument, the rover emitted a melody by controlling the vibrational device that's normally used to agitate samples for analysis. While the sound wasn't audible on Mars due to its thin atmosphere, it was recorded and confirmed back on Earth. This musical demonstration served an important engineering purpose. SAM, which is primarily designed to analyze Martian soil and atmosphere, also had its ability to produce specific frequency outputs. Tested, it verified the vibrational actuator's functionality in the harsh Martian environment. Though this experiment was outside SAM's usual scientific duties, it provided valuable data for instrument calibration. In particular, it showed how SAM can produce precise vibrations, a crucial aspect of ensuring accurate spectrometry measurements. The ability to generate controlled tones helped assess the resilience of the rover's components, particularly in Mars' low-pressure, cold conditions. While the birthday song was more symbolic than scientific, it increased public interest and engagement with the Curiosity mission. The media highlighted the emotional aspect of the gesture, but the engineering team kept its focus on the operational goals. The SAM suite, which plays a central role in analyzing Martian gases, continued to gather critical data on the planet's climate, geology, and potential for past microbial life. The birthday melody was a creative way to show the rover's versatility and how it can adapt to unforeseen circumstances, even if the gesture itself didn't directly contribute to scientific discoveries. Curiosity's core mission to investigate Mars's habitability, study its climate, and lay the groundwork for future human exploration remained unchanged. The rover pressed on toward Mount Sharp, gathering data from clay-rich and sulfate-rich regions. The birthday event was a small but fascinating testament to the rover's ability to perform non-standard tasks and adapt to different scenarios. It also highlighted how well the team could program commands in advance, allowing for flexibility even in the face of unexpected situations. This adaptability is crucial when communication delays mean that every command must be carefully planned. Curiosity's success didn't just depend on its ability to send data back to Earth. It also required ensuring that all systems remained in working order. Even now, over a decade after its landing, Curiosity continues to send back high-resolution data, with instruments like SAM, ChemCam, and MASTCAM still operational. Each non-standard operation, like the birthday song, offers additional insights into the rover's longevity and operational resilience. It's a reminder of the challenges faced when controlling systems millions of kilometers away, and how even seemingly small events can provide valuable technical data. Turning our attention to a different part of the universe, let's talk about WASP-193b, an exoplanet that's gained attention for its remarkably low density. Discovered by the Wide-Angle Search for Planets WASP survey, this planet has a size comparable to Jupiter, but only about 14% of its mass. Its density is incredibly low, about 0.06 grams per cubic centimeter, which is even less than the density of cotton candy. This ultra-low density raises questions about current models of gas giant formation and structure. WASP-193b orbits a Sun-like star roughly 1,200 light-years away. Its orbital period is incredibly short, just 6.25 days, placing it in the category of hot Jupiters, which are gas giants that orbit very close to their stars. The intense radiation from its host star likely heats the planet's atmosphere, causing it to expand and decrease in density. This effect, which is seen in other hot Jupiters, is particularly extreme in WASP-193b. To measure the density of exoplanets, like WASP-193b, scientists use a combination of transit and radial velocity data. When the planet passes in front of its star, it causes a dip in the star's brightness, which reveals the planet's size. Radial velocity measurements detect the tiny wobble of the star caused by the planet's gravity, which helps determine its mass. Combining both measurements allows scientists to calculate density. For WASP-193b, its unusually low mass compared to its size immediately raised eyebrows, placing it in the rare category of ultra-low density exoplanets. Dvovehitim de possibiltum vetis and warden amains upon. The internal structure of WASP-193b remains a mystery due to its strange density. Standard models for gas giants predict a denser core surrounded by layered gas envelopes. However, the planet's low mass suggests it may have little to no core at all. Instead, its composition is likely dominated by hydrogen and helium in a highly diffuse expanded form. Some researchers suggest that additional heat sources, like tidal heating or internal dissipation, could be responsible for the planet's puffed-up atmosphere, though this is still under investigation. WASP-193b is an excellent candidate for future atmospheric studies. Its large size makes it easier for telescopes to analyze its atmosphere and search for chemical signatures. The upcoming James Webb Space Telescope could provide valuable insights into the planet's composition, looking for compounds like water vapor, methane, and carbon monoxide. Spectral analysis during the planet's transits could help scientists determine its atmospheric composition and temperature, offering clues about the processes driving its expansion. The size of WASP-193b makes it an ideal candidate for high-resolution studies. The planet's unusual density has caused scientists to rethink existing theoretical models. Planetary inflation, the phenomenon of a planet's atmosphere expanding due to intense heating, remains an unresolved issue in astrophysics. Various proposed mechanisms, including stellar radiation, internal heat transfer, and inefficient cooling, are being explored. WASP-193b provides a critical test case for refining these models, as its mass and size sit at the outer limits of what is known for gas giants. By comparing it to similar exoplanets, researchers hope to identify the dominant factors that contribute to its extreme structure. The existence of WASP-193b suggests that gas giants can take on far more diverse forms than previously thought. It challenges the long-held belief that the size and mass of a planet are closely linked. This discovery underscores the importance of atmospheric dynamics and the star's influence in shaping a planet's characteristics. It also raises questions about how such a planet might evolve. Researchers are investigating the planet's migration history, how much atmosphere it might have lost, and its long-term stability under the influence of its host star. WASP-193b may help refine models of how mass and radius correlate for exoplanets. Another area of interest is the stability of such a low-density planet. With its expanded atmosphere, WASP 193b is susceptible to atmospheric escape, meaning that intense stellar radiation could strip away its outer layers over time. Despite this, the planet has likely maintained its bloated structure for billions of years. Understanding how it manages to keep its atmosphere intact will provide valuable insights into the longevity of planetary atmospheres under extreme conditions. Observing mass loss rates through ultraviolet and infrared measurements could clarify how the planet's atmosphere is being affected. Turning to Saturn, it's home to one of the most unique atmospheric features in the solar system, a persistent hexagonal pattern at its north pole. This extraordinary shape, first observed by the Voyager spacecraft in the 1980s, was later confirmed with high-resolution images from the Cassini mission. Unlike surface features, this hexagon is a long-lived atmospheric pattern formed by jet streams. It rotates in sync with Saturn's internal rotation and measures about 30,000 kilometers in diameter. Its stable geometry and six-sided shape make it one of the most bizarre weather phenomena in our solar system. The hexagon forms in Saturn's upper troposphere, where winds reach speeds of up to 320 kilometers per hour. It's thought to result from a standing wave pattern created by the high-speed jet streams. Scientists have recreated similar shapes in laboratory experiments, where fluids rotating in cylindrical containers at different speeds form polygonal shapes, including hexagons. The difference in rotational speeds between Saturn's atmospheric layers creates the conditions for this pattern to emerge. The fact that the hexagon has remained stable for decades suggests a finely balanced interaction of energy input and flow confinement. Unlike transient weather patterns on Earth, Saturn's hexagon has remained remarkably constant over the years. Cassini's close flybys provided invaluable data on how the hexagon behaves and evolves. The seasonal changes on Saturn, which orbits the Sun once every 29.5 years, slightly affected the hexagon's visibility. During the northern winter, the region was shrouded in darkness, making it difficult to observe. However, as the planet moved into spring and summer, improved lighting allowed for more detailed imaging. Cassini's mission captured changes in cloud patterns within the hexagon, and infrared observations revealed that the hexagon extends deep into Saturn's atmosphere. These temperature differences drive vertical circulation within the atmosphere, helping to stabilize the structure of the hexagon. The central vortex of the hexagon behaves much like a terrestrial hurricane, but on a much larger scale. Unlike Earth's cyclones, Saturn's vortex remains fixed over the pole. Studying this feature offers insights into planetary atmospheric behavior, particularly on gas giants. Spectral analysis of the hexagon's region has revealed different chemical compositions inside and outside of it. This suggests that the hexagon creates atmospheric mixing barriers, trapping certain chemicals and excluding others. Similar to Earth's polar vortex, Saturn's hexagon also affects the distribution of haze and color. The interaction of sunlight with Saturn's atmosphere leads to photochemical reactions that alter the hexagon's appearance over time. By tracking individual cloud features within the hexagon, scientists measured wind speeds, vorticity, and wave behavior in great detail. The data confirm that the hexagon is essentially a wave-like disturbance superimposed on a fast-moving jet stream. Its persistence depends on the precise velocity gradients between adjacent atmospheric bands. If these gradients were to change, the hexagonal pattern would likely collapse or shift. The stability of the hexagon over decades suggests a long-term balance in Saturn's atmospheric energy. This feature remains one of the most compelling natural laboratories for studying planetary wave mechanics. One intriguing mystery is why Saturn's south pole doesn't exhibit a similar polygonal structure. The South Pole is home to a massive hurricane-like vortex, but it lacks the hexagonal pattern seen at the North Pole. This discrepancy may be due to differences in solar heating, internal heat flow, or asymmetries in Saturn's atmospheric structure. Understanding the contrast between the two poles could offer valuable insights into planetary symmetry and atmospheric dynamics. Data from both poles will help scientists identify the key variables that influence the formation of such stable wave patterns. Further modeling is needed to explore the precise conditions required for such structures to form and remain stable. While the hexagon's overall shape is stable, it is also a dynamic system. The region is home to several smaller cloud features that rotate independently within the hexagonal boundary. Some of these clouds interact with the surrounding atmosphere, creating turbulence and eddying motions. Cloud tracking algorithms applied to Cassini's imagery revealed the presence of filamentary structures and interactions between these smaller features. The hexagon's stability doesn't mean it's static inside its boundaries. There is ongoing movement and activity. Additionally, high-altitude hazes above the hexagon have been observed in ultraviolet wavelengths. These hazes are likely the result of photochemical reactions driven by the sun's ultraviolet light interacting with the gases in Saturn's atmosphere. By studying the vertical layering of haze and clouds, scientists are able to learn more about the upper atmospheric structure. Variations in haze density can also reveal how Saturn's atmosphere evolves with the seasons and how compounds are transported through the atmosphere. Together, these observations provide a detailed three-dimensional view of Saturn's polar environment. Combining data from thermal, visible light, and ultraviolet wavelengths helps build a comprehensive understanding of the atmospheric processes that maintain the hexagon. Saturn's hexagonal storm continues to be one of the most fascinating features in planetary science, offering new insights into fluid dynamics and atmospheric behavior on gas giants. Its stability and internal dynamics challenge our understanding of planetary weather systems, and future missions will likely continue to build on these discoveries. Ganymede's layered magnetic environment is truly unique, offering a rare natural experiment in magnetospheric physics. The planet's magnetic field lines are distorted by the immense influence of Jupiter's own field, which leads to reconnection events. These events provide a valuable opportunity to study plasma behavior and electromagnetic interactions in complex systems. By observing these dynamics, scientists can refine the models used for space weather predictions and planetary magnetism. The presence of Ganymede's magnetic field also indicates that the Moon has a differentiated interior, one with a metallic core capable of sustaining convection. Thermal and gravitational models back the idea that beneath Ganymede's layers of rock and ice, there lies a core surrounded by a silicate mantle and a shell of ice. Below the ice is a vast subsurface ocean of liquid water, which could extend hundreds of kilometers deep. The ocean is sandwiched between layers of high-pressure ice, and these layers influence heat transfer and the movement of water. The evidence for Ganymede's subsurface ocean comes from two key observations: the induced magnetic field and auroral behavior. As Ganymede moves through Jupiter's magnetic field, it generates secondary magnetic fields. These variations can only be explained by the presence of a conductive layer, such as a salty ocean. Additionally, ultraviolet observations by the Hubble Space Telescope have shown auroral ovals whose oscillation patterns match models that predict an ocean beneath the surface. These findings strongly suggest the presence of a global ocean that surrounds the entire Moon. Ganymede's subsurface ocean is estimated to be located beneath 150 kilometers of ice, and could be more than 100 kilometers deep. Despite the extreme pressures and temperatures at such depths, the presence of liquid water makes Ganymede a compelling target for studying potential extraterrestrial life. The ocean would remain liquid due to the salts dissolved within it, which lower its freezing point and maintain its conductivity. Furthermore, the chemical interactions between the ocean and the rocky mantle could provide vital energy sources, making Ganymede an interesting location for the search for microbial life. However, unlike Europa or Enceladus, Ganymede shows fewer signs of surface exchange with its ocean. The Moon's surface is heavily cratered, with a mix of dark and bright regions that suggest a long, complex geological history. Tectonic features such as grooves and ridges point to past geological activity, but current surface renewal appears limited. This means that Ganymede's ocean may be more isolated than those of Europa and Enceladus, with fewer opportunities for surface sampling. Nonetheless, these differences offer valuable insights into the characteristics of ocean worlds, and each icy moon presents a unique context for understanding subsurface water. In 2023, the European Space Agency launched the Jupiter Icy Moons Explorer JUICE mission, which will study Ganymede in greater detail. JUICE will perform multiple flybys before entering orbit around Ganymede, making it the first spacecraft to orbit a moon other than Earth's. The mission will map the Moon's surface, analyze its magnetic field, and investigate its interior structure. One of JUICE's primary goals is to characterize the subsurface ocean and its interactions with the ice shell. Instruments aboard the spacecraft will search for water signatures and monitor the local plasma environment. These measurements will help clarify the nature of Ganymede's ocean and dynamo. Ganymede's magnetic field also offers a fascinating case study for understanding planetary interiors. A persistent dynamo requires specific thermal and compositional conditions, and by comparing Ganymede with Earth and Mercury, both of which also have active dynamos, scientists can test core cooling models. This research will improve our understanding of how dynamo activity operates within icy moons as opposed to terrestrial planets, contributing to models of long-term planetary and satellite development. The combination of a magnetic field and subsurface ocean makes Ganymede an exceptional object for scientific study. The magnetic field shields parts of the Moon's surface from charged particle bombardment, potentially preserving volatile compounds. Additionally, Ganymede's interaction with Jupiter's magnetosphere creates dynamic particle environments that influence surface chemistry. These factors, coupled with the ocean's potential for chemical energy, make Ganymede a crucial target in the search for life-supporting environments beyond Earth. While the direct detection of life is unlikely, Ganymede's conditions are within the known habitable range, making it one of the top contenders for future astrobiological research. Shifting focus to Neptune, this distant planet is known for having the most extreme winds in the solar system. Wind speeds on Neptune have been recorded at up to 2,100 km per h, particularly near the equator and mid-latitudes. These winds are far faster than those on any other planet, including Jupiter. For comparison, Jupiter's jet streams reach speeds of about 600 km per h, and Earth's strongest winds during hurricanes rarely exceed 300 km per h. Neptune's extreme wind speeds are particularly notable given its great distance from the Sun, as the planet receives much less solar energy than the other gas giants. Despite the limited solar energy, Neptune maintains a high level of atmospheric energy. This paradox is likely due to internal heat. Neptune emits about 2.6 times more energy than it receives from the Sun. This excess energy, generated by processes like slow gravitational contraction, drives the planet's atmospheric motions. It causes convection in the outer layers of the atmosphere, leading to the formation of zonal winds and stable circulation patterns. With little surface friction to slow them down, these winds can maintain their high speeds across vast areas. Neptune's winds are organized into bands similar to those on Jupiter and Saturn, but the shear between opposing wind bands is particularly strong. In some regions, winds blow westward at high speeds, while adjacent bands move eastward. This differential motion contributes to the formation of large, stable storms, such as Neptune's famous Great Dark Spot. Unlike Jupiter's Great Red Spot, Neptune's dark spots appear and disappear over the course of several years. These transient storms observed by Voyager 2 and the Hubble Space Telescope suggest that Neptune's weather system is much more dynamic than those of other gas giants. The formation and dissipation of these storms are influenced by varying wind patterns, internal heat flux, and changes in atmospheric composition. Winds on Neptune vary with latitude and altitude, forming a complex three-dimensional structure. Near the equator, wind speeds are slower, but they increase significantly at mid-latitudes. Additionally, winds in the upper atmosphere are faster than those at lower altitudes, creating distinct vertical layers. These variations are due to differences in temperature, pressure, and composition at various heights in the atmosphere. Using infrared and visible light observations, scientists have tracked cloud movements and estimated wind speeds. These data are essential for creating dynamic models of Neptune's atmosphere and understanding how energy is transferred both vertically and laterally. The planet's atmosphere is primarily composed of hydrogen, helium, and methane, with methane giving Neptune its distinctive blue color by absorbing red wavelengths and scattering blue light. This methane also plays a role in cloud formation and energy distribution within the atmosphere. Neptune's extreme winds, combined with its high-altitude methane clouds, make it an ideal subject for studying high-velocity wind systems. Voyager 2, which remains the only spacecraft to visit Neptune, provided the first direct measurements of the planet's winds. These measurements have since been supplemented by observations from Earth-based telescopes and the Hubble Space Telescope. Though these follow-up observations are less detailed, they confirm that Neptune's winds remain fast and its storms continue to shift and evolve. Neptune's weather system challenges conventional models, as it maintains powerful winds despite the planet's frigid temperatures, averaging around -214 degrees Celsius. This anomaly shows that internal heat alone can drive vigorous atmospheric activity, providing valuable insights for the study of exoplanets, particularly cold gas giants orbiting distant stars. Understanding Neptune's internal heat flow and atmospheric dynamics can help researchers model the weather on these distant worlds. Neptune's winds not only defy expectations but also deepen our understanding of how planetary climates operate with minimal solar input. The mechanics of these winds involve a combination of pressure gradients, the Coriolis effect, and differential rotation. Neptune's rapid rotation, completing a full spin in about 16 hours, intensifies the Coriolis effect. These forces work together to organize the winds into zonal jets and sustain long-lived storm systems. Computational models simulate how these forces interact with convective motion and radiative cooling, and Neptune provides a perfect testing ground for these theories under extreme conditions. Its cold, distant environment offers a stark contrast to the more solar-powered gas giants, giving us valuable insight into atmospheric dynamics. In a different context, let's imagine a scenario where Earth suddenly stops orbiting the Sun. In this situation, Earth would fall directly into the Sun. The balance between gravitational attraction and Earth's sideways velocity keeps our planet in orbit. If Earth were to stop this orbital motion, gravity alone would pull it toward the Sun. This simple scenario helps illustrate how orbits work. Without the tangential velocity, Earth would begin to fall directly inward, driven only by gravity. To calculate how long it would take for Earth to fall into the Sun, we use Newton's laws of motion. In a vacuum, neglecting other forces, the fall would take about 64.66 days. This calculation assumes the Sun is stationary and Earth moves directly toward it. The result comes from integrating the gravitational attraction between Earth and the Sun, and the fall is not uniform. Initially, Earth would move slowly, gradually accelerating as it gets closer to the Sun. This increase in speed is due to the nature of gravity. It grows stronger as distance decreases. As Earth nears the Sun, it would reach extreme speeds before impacting, with kinetic energy building up significantly in the final stages. Though this scenario is purely theoretical, it serves as a thought experiment to understand gravitational dynamics. The amount of energy needed to stop Earth's orbital motion is astronomically large, roughly 2.7 quaternions 10 circumflex 33 joules. This is far beyond any feasible energy manipulation by natural or artificial means. However, the concept is useful for teaching about the stability of orbits and the importance of motion in maintaining them. If any part of the system, Earth's velocity or the Sun's gravitational pull, were removed, the entire structure would collapse. This model is not just about Earth but applies to any planet or moon in orbit, and it helps explain why orbits are constantly in motion, balancing gravitational pull and orbital velocity. An important aspect of this scenario is that tidal forces would grow stronger as Earth nears the Sun. The gravitational pull would be uneven across the planet's diameter, stretching Earth and potentially causing structural failure long before impact. In the final stages of the fall, the increasing temperatures and solar radiation would vaporize the atmosphere, and the surface materials would begin to ionize. Earth would disintegrate progressively, highlighting the destructive potential of a gravitationally unbalanced system. While this thought experiment excludes the effects of other planetary bodies and solar system dynamics, it remains a helpful tool in understanding orbital mechanics. The full-time model is a simplified version of reality that illustrates how gravitational acceleration works. The closer an object is to a massive body, the faster it falls. This principle is key in understanding planetary interactions and spacecraft trajectories. It also teaches the concept of gravitational potential energy. When an object moves in orbit, Its energy is split between kinetic and potential energy. If orbital motion stops, the potential energy transforms entirely into motion, speeding up the object. This transformation is governed by the conservation of energy, a fundamental principle in physics. In a more grounded scenario, Jupiter, the largest planet in our solar system, holds fascinating features. With a mass over 300 times that of Earth, Jupiter is a colossal gas giant with a diameter of around 143,000 kilometers. Despite its size, Jupiter lacks a solid surface and is composed mostly of hydrogen and helium, with a thick atmosphere that gradually transitions into deeper layers. Unlike terrestrial planets, Jupiter doesn't have distinct layers, but is organized by density and pressure as you move inward. This structure influences everything from weather patterns to the planet's magnetic field. The upper atmosphere of Jupiter is a dynamic system filled with ammonia crystals, which form colorful bands and zones. These features are driven by jet streams reaching speeds of over 500 kilometers per h. Beneath this visible atmosphere, there's a denser region of molecular hydrogen where pressure increases dramatically. As you go deeper, hydrogen transitions into a supercritical fluid state, where the boundary between gas and liquid is blurred. Further down, at extremely high pressures, hydrogen becomes metallic, a state in which atoms are packed so tightly that their electrons are free to move, creating a conductive fluid capable of generating magnetic fields. Jupiter's immense magnetic field arises from this metallic hydrogen layer, creating the strongest planetary magnetic field in the solar system. This field influences charged particles across a vast region, interacting with the planet's moons and surrounding space environment. The existence of metallic hydrogen was theorized in the 1930s, but its properties weren't confirmed until more recent experiments. These experiments aim to replicate the extreme pressures and temperatures found in Jupiter's interior, helping to validate our understanding of this exotic state. Jupiter's internal heat is another remarkable feature. The planet radiates more energy than it receives from the Sun, suggesting that gravitational contraction and other thermal processes are ongoing. This internal energy fuels atmospheric motion and may play a role in storm formation. The lack of a solid core means that Jupiter's structure is continuously layered by pressure and composition, rather than clear boundaries. Below the metallic hydrogen, there may be a rock metal core, though its size and nature are still unclear. Some models propose that the core is diffuse, partially dissolved in the surrounding hydrogen, rather than solid. Data from the Juno spacecraft has refined our understanding of Jupiter's interior. Through gravity and magnetic measurements, we've learned that the planet's interior is more complex and layered than previously thought. This ongoing research helps us understand not only Jupiter's structure but also the behavior of other gas giants in the universe. Jupiter's lack of a solid surface means that objects falling into it simply sink deeper into its dense atmosphere. There's no ground to crash into. Instead, as they descend, they are crushed and heated by the rising pressure, eventually breaking apart. This unique characteristic makes landing on Jupiter impossible for any spacecraft. They would be destroyed long before reaching its core. This also makes direct exploration of its deeper layers challenging. To study Jupiter, missions must rely on remote methods like gravity data, magnetometer readings, and other measurements. The Juno spacecraft, for example, continues to orbit Jupiter, collecting valuable data from its poles. One of the most fascinating features of Jupiter is the presence of metallic hydrogen. Only a planet of Jupiter's massive size and pressure could create such a state of matter. This makes the planet a natural laboratory for studying high-pressure physics. Learning how hydrogen behaves in such extreme conditions is crucial for planetary science and materials research. It also helps us understand other gas giants and brown dwarfs, which likely share similar internal compositions and may also have metallic hydrogen layers. Jupiter's lack of a surface also affects its weather patterns. The Great Red Spot, a massive storm on the planet, remains stable for centuries. Without a solid surface to slow it down, the storm is free to persist, circulating in the upper layers of Jupiter's atmosphere. The deeper regions of the planet have no solid boundary to create friction, which allows the storm to remain strong. Rising heat from the interior creates complex vertical movements, causing turbulent, layered flows. These processes are hard to replicate on Earth, making Jupiter an exceptional case for studying atmospheric dynamics. The planet's unique fluid structure stands apart from anything we see elsewhere in the solar system. Speaking of space missions, NASA's DART mission demonstrated an incredible step forward in planetary defense. In 2022, it collided with the small moonlet Dimorphos, which orbits the asteroid Didymos. This collision was part of a test to see if we could alter an asteroid's trajectory to prevent a future impact on Earth. Although Dimorphos posed no threat, this mission provided vital data. The spacecraft, traveling at around 22,000 kilometers per bit rate, crashed into Dimorphos, significantly changing its orbit. Before the impact, Dimorphos completed an orbit around Didymorph every 11.92 hours. After the collision, this period shortened by 32 minutes, an impressive and measurable result. This successful test confirmed that we can use kinetic impactors, rather than explosives, to change the path of an asteroid. The DART spacecraft carried a single instrument, the Draco camera, which guided its approach. The camera sent images back to Earth in real time, allowing mission control to see Dimorphos in increasing detail. In its final moments, DART used autonomous navigation to ensure a direct hit on the asteroid. The collision resulted in a plume of debris visible from Earth and space telescopes. This cloud of material helped scientists measure how much momentum was transferred during the impact. To observe the change in Dimorphos's orbit, astronomers used ground-based telescopes. They watched how the asteroid dimmed as it passed in front of Didymos, which allowed them to calculate the updated orbital period. The results exceeded expectations, proving that even small changes in the trajectory of an asteroid can be significant. Additionally, the impact's effectiveness was amplified by the momentum created by the debris ejected from the asteroid. This phenomenon is known as momentum multiplication. Another part of the mission was the LI-THEOCUBE, a small satellite deployed from DART before the impact. It flew past Dimorphos minutes after the collision, capturing images of the impact and the resulting debris cloud. LICA-CUBE worked autonomously, sending back data over the following weeks. These images revealed fascinating details, like filaments and streams in the ejector, and provided valuable insights into Dimorphos's surface and composition. The DART mission is just the beginning of efforts to protect Earth from potential asteroid impacts. While Dimorphos posed no danger, testing this technique on a real target was essential. The success of the mission will help improve our ability to detect, track, and target dangerous asteroids in the future. The data collected will refine our simulations of how to deflect asteroids, an essential part of planetary defense planning. In the future, ESA's HIA mission, scheduled for launch in 2024, will revisit the Didymos system to study the aftermath of DART's impact. HIA will conduct in-depth surveys of Dimorphos's shape, mass, surface, and crater, providing further insight into the effects of the collision. It will also deploy CubeSats to examine the internal structure and composition of the asteroid. The mission's goal is to assess the stability of the orbit change and understand how craters form in low gravity. The success of DART and LICA-CUBE has highlighted how important surface properties are when it comes to impact efficiency. A porous, loose surface produces more ejecta, which increases momentum transfer and makes the redirection more effective. In contrast, a denser surface would absorb more of the impact's energy, reducing the effect. The data from this mission has helped confirm theories about how surface materials behave in low-gravity environments, and will shape future mission planning. Modeling the gravitational interactions between Didymos and Dimorphos was critical for understanding the dynamics of the binary asteroid system. The results showed that even small changes in orbital energy can produce detectable effects in such systems. This level of precision is essential for applying this method to larger or more hazardous targets. Understanding how momentum is transferred in binary systems will help refine long-term impact strategies and improve our general knowledge of asteroid dynamics. When it comes to solar science, the time it takes for light to reach Earth from the Sun is crucial for understanding how we observe solar events. Light takes about 8 minutes and 20 seconds to travel from the Sun to Earth. This delay is due to the vast distance between us and the Sun, roughly 149.6 million kilometers, or 1 astronomical unit. The speed of light is constant, traveling at approximately 299,792 kilometers per second, so this travel time is always the same. This delay means that when we observe the sun, we're actually seeing it as it was over 8 minutes ago. The same principle applies to all forms of electromagnetic radiation, including heat and ultraviolet light. For solar weather prediction, this lag must be accounted for, as it impacts how we correlate visual data from the sun with space weather effects here on Earth. Interestingly, the light we see from the sun doesn't come directly from its surface. Instead, it originates deep within the sun's core, where nuclear fusion occurs. The fusion process releases energy in the form of photons, which begin their long journey outward. Within the sun, these photons undergo countless scatterings before eventually reaching the surface, which can take thousands to millions of years. Once they reach the surface, however, the photons make their way to Earth in just 8 minutes and 20 seconds. This contrast between the production and travel of light emphasizes the difference between the sun's interior and what we observe from Earth. The time it takes for sunlight to reach Earth plays a crucial role in defining the astronomical unit AU, a measurement that's fundamental in celestial mechanics and planetary movement calculations. The speed of light is constant, so the time it takes for light to cross 1 AU serves as a handy reference for calibrating scientific instruments and syncing observations. This is especially important in the realm of space exploration, where it influences everything from spacecraft navigation to timing solar eclipses. Understanding the Earth-Sun distance allows for precise modeling of orbital mechanics, forming the backbone of modern space science and engineering. Solar radiation that reaches us spans a broad spectrum, ranging from infrared to ultraviolet. Remarkably, all these types of radiation travel through space at the same speed, meaning they all hit Earth simultaneously. The 8 minutes and 20 seconds it takes for sunlight to travel from the sun to Earth applies not just to visible light, but to the entire spectrum of solar emissions. Though different wavelengths of sunlight might be absorbed or scattered differently by Earth's atmosphere, this doesn't change their travel time. This uniformity in how light moves through space is a fundamental principle of the electromagnetic wave model, which asserts that all forms of light, regardless of their color or energy, follow the same path and reach us in the same amount of time. This same concept has profound implications for astronomers studying objects beyond our solar system. When we observe stars, galaxies, and distant celestial bodies, we're always seeing light from the past. The further away an object is, the longer its light has taken to reach us, meaning that the images we see are always behind real-time events. In this context, the 8-minute delay for sunlight is almost negligible, a tiny blip compared to the vast distances between us and other galaxies. However, this concept helps us understand much larger ideas in cosmology, like look-back time and the observable universe, where we explore how time and space intertwine through the travel of light. For space missions, this light delay becomes a practical issue that needs to be accounted for. The changing distance between Earth and the Sun throughout the year affects how we communicate with spacecraft. Mission control must constantly predict and adjust for these delays in real time to ensure smooth data transmission. Similarly, when observing solar phenomena using satellites, scientists must account for this 8-minute lag to ensure their instruments are calibrated correctly. This delay is crucial for accurate timing and triangulation in studies of heliophysics. For example, when solar flares or coronal mass ejections and CMEs erupt, instruments on Earth or in near-Earth orbit detect these events after the 8-minute delay, but the charged particles associated with these eruptions travel more slowly and can take hours to reach Earth. This delay provides a vital window of time to protect astronauts, satellites, and other infrastructure. This gap between light and particle travel is essential for developing reliable space weather forecasting systems. The initial light signal serves as an early warning, alerting us to solar activity before its physical effects are felt on Earth. This principle also helps astronomers accurately timestamp solar events in their records. By knowing when the light from solar events arrives on Earth, researchers can reconstruct the conditions on the Sun at the time of the event. With data from other spacecraft, these timestamps allow scientists to cross-reference and synchronize observations across various instruments and wavelengths. The 8-minute light delay becomes a consistent reference point, aligning data streams and enabling international collaborations on solar monitoring. This delay in sunlight isn't just a technicality, it also reinforces a fundamental concept in astronomy. We never observe the present in space, even within our own solar system. Every observation is delayed by the time it takes for light to travel. The 8-minute and 20-second delay from the Sun to Earth illustrates the enormous scale of our cosmic environment. It serves as a reminder that the universe operates on timescales far beyond our everyday experience, making it easier to grasp how light, time, and distance interact in space. Understanding this constant gives us a clearer sense of how we perceive and study the universe. Now let's shift to the Oort cloud, a theoretical structure that might extend as far as 100,000 AU from the Sun. Though it's never been directly observed, the Oort cloud is believed to be a massive spherical shell of icy objects that surrounds our solar system. Unlike the Kuiper belt, which lies beyond Neptune, the Oort cloud starts much farther out, possibly around 2000 AU, and stretches all the way to 100,000 AU, which is roughly 1.5 light-years from the Sun. This places it at the very edge of the Sun's gravitational influence. Beyond this point, the Sun's gravity weakens, and interstellar space takes over, meaning that objects would no longer be bound to the solar system. The idea of the Oort cloud was first proposed by Dutch astronomer Jan Ode in 1950. He observed that long-period comets, which have orbits lasting thousands of years, seem to appear from every direction in the sky. This uniform distribution of comets suggested a spherical source region surrounding the solar system. The comets' orbits and velocities indicated that they originated from far beyond the planetary region. Oort hypothesized that a distant reservoir of icy objects, possibly disturbed by the gravitational influence of passing stars or the galactic tides, could send some of these objects into the inner solar system. The size of the Oort cloud is estimated based on the Sun's gravitational reach. At around 100,000 AU, the Sun's gravity weakens significantly, and the influence of the galaxy becomes comparable. This outer region, known as the Hill sphere, defines the boundary where the Sun can still hold objects in orbit. Beyond this, objects are no longer gravitationally bound to the Sun. The inner part of the Oort cloud, sometimes called the Hills cloud, may extend from 2,000 to 20,000 AU, though these distances are theoretical and based on orbital models. No spacecraft has ventured far enough to reach the Oort cloud, and the farthest human-made object, Voyager 1, is currently just 160 AU from the Sun, about 16% of the way to the cloud's outer edge. At the spacecraft's current speed, it would take tens of thousands of years to reach the Oort cloud. This vast distance, combined with the small size and low reflectivity of the objects within it, makes direct observation nearly impossible with today's technology. Even the largest telescopes on Earth cannot detect objects that far unless they are actively outgassing, like comets. Though we can't observe the Oort cloud directly, scientists infer its existence by studying long-period comets that travel from distant origins. The paths of these comets suggest they come from a region much farther than the Kuiper belt. Simulations of the Oort cloud's orbital dynamics support the idea of a distant spherical cloud of icy bodies. Occasionally, a comet will be perturbed and fall inward toward the Sun, becoming visible as it nears our star. These rare events offer indirect evidence that a reservoir of icy material exists at great distances from the Sun. Finally, models of the Oort cloud suggest that interactions with nearby stars and the galactic environment play a significant role in the cloud's behavior. As our solar system orbits the center of the Milky Way, it encounters varying gravitational forces which can disturb the orbits of objects in the Oort cloud. These disturbances can send some of these objects into the inner solar system, where they may be observed as comet showers, brief but fascinating glimpses of this distant icy reservoir. These events might have taken place throughout Earth's history, with statistical analysis of crater ages, offering clues to potential links between impacts and Oort cloud activity. Understanding these cycles is essential for assessing long-term risks associated with impacts. Some models suggest that the Oort cloud could be divided into two main regions, the outer spherical cloud and an inner, denser toroidal region. The outer part of the cloud is more vulnerable to galactic disturbances, while the inner region, which is more tightly bound to the Sun, remains relatively stable. This structure helps explain the differences in comet origins and their frequency. The inner region may also act as a replenishing source for the outer cloud, replenishing it over time. However, these dynamics remain a topic of active research and are still theoretical, pending further observational data. Turning to a more distant phenomenon, the APE system, located roughly 8,000 light-years away, features an extraordinary and rare triple star configuration. The system's core consists of a pair of Wolf-Rayet stars, massive stars that shed enormous amounts of material due to their intense stellar winds. Surrounding this binary system is a third, more distant companion star. Infrared observations have revealed a remarkable spiral structure of dust streaming away from the central binary. These spirals, shaped by the interaction of stellar winds in a binary orbit, resemble tightly wound coils. The system was named after the Egyptian serpent god of chaos, reflecting its dynamic and turbulent nature. Wolf-Rayet stars are known for their high temperatures and massive mass loss through stellar winds. In the case of the APE system, these winds can reach speeds of up to 12 million kilometers per hour. When two such stars orbit closely, their winds interact to form a pinwheel-shaped spiral, a phenomenon observed in some binary systems. However, the APE system's spiral is unusually large and highly asymmetric. The disparity in speed between the expanding dust and the interstellar winds suggests a strong directional bias in the emission of these winds. This unique structure offers an ideal case study for understanding wind-driven mass ejection. The system was first observed in detail using the Very Large Telescope VLT in Chile, which captured high-resolution images of the dust spirals. These spirals are not static. They're constantly evolving, with new material being ejected as the stars orbit each other, tracing their motion over time. The dust in the system emits strongly in the infrared spectrum, revealing structures that are not visible in optical light. The velocity of the winds and the system's angular momentum influence the appearance and extent of the spiral arms. A particularly striking aspect of the AP system is the mismatch between the direction of the spiral dust and the motion of the stellar winds. The infrared dust expands much more slowly than the fast-moving polar winds. This discrepancy suggests that the winds are highly directional, moving faster along the poles and more slowly along the equatorial plane. This results in a distorted outflow pattern, deviating from a uniform spherical shell. This unique configuration challenges existing models of wind symmetry in massive stars and may indicate the presence of rapid stellar rotation. Rapid rotation in Wolf-Rayet stars is believed to be a key factor in producing long-duration gamma-ray bursts, GRBs, when these stars collapse. The conditions observed in AP resemble those expected just before such a collapse, with a rapidly rotating mass-losing star. This has led to speculations that AP could be a progenitor of a GRB, though confirmation would require long-term monitoring. Regardless, the AP system provides a valuable real-world testbed for studying the final stages of massive star evolution. The material ejected from AP plays a significant role in enriching the interstellar medium. As these stars lose mass, they release heavy elements like carbon and oxygen, elements formed through nucleosynthesis in the star's cores. These materials are crucial for the formation of new stars and planets, seeding the galaxy with the building blocks of future generations of celestial bodies. Over time, the cumulative output from systems like AP contributes to the galactic recycling process, where stellar death feeds the creation of new stars and planetary systems. The presence of a third star in the AP system adds another layer of complexity to its dynamics. This outer companion star likely influences the orbits of the central binary pair through gravitational interactions. These interactions cause the orbits of the stars to shift over time, potentially altering the pattern of wind interactions and dust formation. Triple star systems like AP are relatively common among massive stars, and studying them provides valuable insights into how such systems affect mass loss and angular momentum distribution. Time domain observations of the AP system are essential for understanding its evolution. The expansion of the dust spirals provides a means for astronomers to estimate wind speeds and material ejection rates. Infrared monitoring allows scientists to track the evolution of the outer structures, while spectroscopy gives insights into the composition and velocity of the winds. By comparing current observations with past data, researchers can reconstruct the recent history of mass loss, offering a dynamic view of stellar evolution. This time-lapse approach bridges the gap between theoretical models and actual observations in high-mass star systems. The winds and spirals of the AP system are not just visually striking phenomena, they serve as probes into the physics of radiation-driven outflows. The interaction between radiation pressure, stellar rotation, and gravity determines the structure of these winds. Understanding how energy and mass are distributed across different directions will refine our models of radiative transfer and angular momentum loss in massive stars. These processes are essential for predicting how massive stars evolve when they explode and what remains after their collapse. The APE system provides a high-resolution example of these mechanisms at work, offering invaluable data for improving our understanding of stellar physics. Shifting focus to Mars, the planet experiences planet-wide dust storms that can be so intense they completely cover the planet. These global dust storms, or planet-encircling storms, occur sporadically and can last for weeks or even months. When they happen, they obscure the Martian surface, lifting fine particles into the atmosphere. Unlike smaller, localized dust storms that occur throughout the Martian year, these global storms have a significant impact on the atmosphere and can disrupt robotic missions on the surface. The primary driver of these dust storms is solar heating. Mars has a thin atmosphere composed mostly of carbon dioxide, and as sunlight heats the surface unevenly, it creates pressure differences that lead to strong winds, especially during the southern hemisphere's summer, when Mars is closest to the Sun. These winds lift dust particles from the surface, and as the dust becomes airborne, it absorbs sunlight, heating the surrounding air. This heating creates even stronger winds, lifting more dust in a feedback loop that causes the storms to rapidly grow in size. Martian dust is exceptionally fine and cohesive, often compared to talcum powder in texture. Because of its small size and the low gravity on Mars, these particles can remain suspended in the atmosphere for extended periods. The lack of moisture or vegetation means there is nothing to trap or stabilize the dust, allowing it to remain airborne for long stretches. When dust storms occur, the particles scatter sunlight, reducing visibility at the surface. During a global storm, the sunlight at the Martian surface can drop dramatically, affecting solar-powered instruments and rovers. Global dust storms on Mars are rare, but when they do occur, they typically begin in the southern hemisphere. The storms often start in known storm genesis zones, like Hellas Basin or the northern tropics, and gradually expand outward. Once large enough, these storms can encircle the entire planet in just a few days. The dynamics of these storms are influenced by seasonal shifts and temperature contrasts between the hemispheres. These conditions determine how dust moves vertically and horizontally within the atmosphere. Understanding how these regional storms evolve into global phenomena is a key focus in Martian climatology. The temperature differences between the dusty upper atmosphere and the cooler surface alter the structure of the Martian air column. This change in temperature causes the atmospheric circulation to shift from its usual zonal flow to a more chaotic pattern. Dustier particles rise tens of kilometers into the air, forming thick, optically dense layers that increase infrared emission and contribute to atmospheric heating. This heating alters pressure gradients and disrupts typical wind patterns on the planet. Observations from spacecraft like the Mars Reconnaissance Orbiter and MAVEN have provided essential data on storm evolution. These satellites monitor temperature, dust opacity, and wind patterns across different atmospheric layers, helping scientists model how dust storms develop and their effects on Martian atmospheric chemistry. Dust storms also influence the distribution of water vapor and trace gases, affecting their transport across the planet. By tracking changes in surface albedo and observing how dust settles after storms dissipate, researchers can refine their understanding of Martian weather systems and their long-term impact on the planet's environment. Data from Mars rovers like Curiosity and Perseverance play a key role in predicting dust storms. These rovers monitor sunlight, air pressure, and temperature changes during storms. Their findings help validate what we observe from orbit. Even in regional storms, we can see drops in solar power and temperature shifts. This helps us understand when smaller storms could grow into larger ones. Though Martian dust storms aren't typically destructive in terms of wind strength, the dust can damage equipment, affect power generation, and impact operations. Long-term missions will need strategies to manage this dust. The Sun and Moon appear nearly the same size from Earth, a rare coincidence. The Sun is about 400 times larger than the Moon, but it's also 400 times farther away, making them appear the same size in the sky. This alignment is why total solar eclipses happen, where the Moon can fully cover the Sun. However, the Moon's distance from Earth varies slightly, causing its apparent size to change. In some cases, the Moon doesn't cover the Sun completely, leading to an annular eclipse where a bright ring is visible. Over time, the Moon is slowly moving away from Earth, and eventually, it will be too small to block the Sun, ending total eclipses. This rare alignment also affects how we observe the Sun. During eclipses, when the Sun's bright light is blocked, we can see the solar corona, which is usually hidden. Studying the corona helps scientists understand solar wind, magnetic fields, and high-energy processes. Eclipses have been crucial in scientific breakthroughs, like testing Einstein's theory of general relativity during the 1919 solar eclipse, confirming the bending of light around the Sun. Such events are only possible because the Sun and Moon appear so similar in size. Venus has an unusual atmosphere that rotates much faster than the planet itself. The surface of Venus rotates slowly, taking 243 Earth days for one full rotation, while its upper atmosphere completes a rotation in just 4 Earth days. This phenomenon, known as superrotation, causes winds that reach speeds of up to 360 km per BRT. These fast winds are about 60 times faster than the planet's rotation and create complex weather patterns. The cause of Venus's superrotation is still not fully understood, but theories suggest it could be due to solar heating and atmospheric waves that push wind patterns. Despite the thick carbon dioxide atmosphere and high surface pressure, superrotation happens mainly in the upper atmosphere, where the air is less dense. Below 50 kilometers, winds slow down significantly. This fast-moving atmosphere helps evenly distribute heat, causing Venus to have nearly the same temperature across its surface, around 470 degrees Celsius, day and night. Venus's superrotation also affects its clouds, stretching them into long bands. These clouds can form waves, especially near the equator, due to the interaction of winds with the planet's weather systems. Long-term observations are helping scientists understand how Venus's winds and climate change over time. These studies not only help us understand Venus, but also inform our knowledge of other planets like Titan, Saturn's moon, which shows similar atmospheric behavior. Venus is a natural laboratory for testing climate models under extreme conditions. Venus's slow rotation and thick atmosphere create unique dynamics that are not found on Earth. Understanding these behaviors is important for studying atmospheric conditions on other planets. Models trying to simulate Venus's superrotation need to account for complex factors like fluid dynamics, radiative transfer, and chemical interactions. These models require high-resolution data on temperature, pressure, and wind patterns at various altitudes. However, current models still struggle to fully match the speed and stability of Venus's winds, so more observations and data are needed. The Sun's corona is much hotter than its surface, reaching temperatures over 1 million degrees Celsius, while the visible surface, the photosphere, is around 5,500 degrees Celsius. The surprising temperature difference has puzzled scientists for a long time. The corona is only visible during total solar eclipses, or with special instruments appearing as a faint halo stretching millions of kilometers into space. The temperature of the corona indicates that the heat isn't radiating outwards from the Sun, but is actively transferred or generated in the upper layers. Understanding this heating is key to predicting solar activity, which affects the solar system. One leading theory to explain the corona's heating is magnetic reconnection. The Sun's magnetic field often gets tangled, and when the field lines break and reconnect, they release huge amounts of energy. This energy could transfer heat from the lower atmosphere into the corona. Other theories involve waves like Alfvén waves, which carry energy upwards from the sun's interior. These waves may be responsible for heating the corona, though it's still unclear how efficiently they can dissipate energy. The corona is made of plasma, a hot ionized gas that emits strongly in the ultraviolet and X-ray regions. This makes it difficult to observe without space-based telescopes like the Extreme Ultraviolet Imaging Telescope and X-ray telescopes. The sun's magnetic field shapes the corona's structure, with areas where the magnetic field lines open into space, called coronal holes, being cooler and darker. These holes are major sources of fast solar wind. The sun's activity changes in an 11-year cycle, affecting the dynamics of the corona and influencing space weather near Earth. Coronal mass ejections, CMEs, are large eruptions of plasma and magnetic fields from the corona. When directed at Earth, CMEs can disrupt satellites, communications, and power grids. Understanding the corona's heating and magnetic structure is essential to predicting these events. Missions like NASA's Parker Solar Probe, launched in 2018, are getting closer to the sun than any previous mission, collecting data to help scientists refine models of the sun's behavior and energy movement. The moon is slowly moving away from Earth, about 3.8 centimeters each year. This change is caused by tidal interactions between Earth and the moon, where Earth's gravity pulls on the moon, pushing it into a higher orbit. Over billions of years, this has caused the moon to slowly move farther away, and Earth's rotation has also slowed down. The current rate of lunar recession is not constant and has changed over time. In the past, the moon was much closer to Earth, and days were shorter. As the moon moves away, its apparent size in the sky decreases. This will eventually make total solar eclipses impossible, leaving only annular or partial eclipses. This transition will happen gradually, over millions of years. Even though the moon is receding, total eclipses will continue for a long time. This slow change is already observable, as some solar eclipses are now annular, happening when the moon is farther away from Earth in its orbit. The distance between Earth and the moon also affects the timing and frequency of eclipses. As the moon moves farther away, the conditions for perfect alignment between the sun, moon, and Earth become less common. This shift in eclipse patterns is a natural result of the moon's orbit. The study of lunar recession helps us understand broader planetary dynamics and its effects on Earth's climate and habitability. The moon stabilizes Earth's axial tilt, and this stabilization might also change over time. Monitoring the moon's motion through experiments like laser ranging provides crucial data on how the Earth-Moon system evolves. The precision of lunar measurements allows scientists to track the moon's orbit with millimeter accuracy. These data help refine gravitational models of the Earth-Moon system and test theories of general relativity. In July 1994, comet Shoemaker-Levy 9 collided with Jupiter, leaving massive scars on the planet. This was the first time an extraterrestrial collision was directly observed. The comet had been captured by Jupiter's gravity years earlier and broke apart. In 1994, its fragments collided with Jupiter's atmosphere at speeds of 60 kilometers per second, creating dark scars visible in both visible and infrared wavelengths. These scars, larger than Earth, were observed for weeks and allowed scientists to study high-energy impacts on planetary atmospheres. Olympus Mons, the tallest mountain in the solar system, is located on Mars. It rises about 22 to 25 kilometers, nearly 3 times the height of Mount Everest. This massive shield volcano is found in the Tharsis volcanic region, and its size is due to Mars's lower gravity and lack of plate tectonics. The volcano grew over millions of years from repeated lava flows, allowing it to accumulate great height. Its slopes are gentle but dramatic cliffs up to 8 kilometers high surround the base. The caldera at the top, about 80 kilometers wide, reveals the volcano's long history of eruptions. Recent evidence suggests it may still be dormant, not extinct. Olympus Mons's surrounding escarpment shows signs of past collapse, with debris flows and landslides at its base. This volcanic region, along with others like Asgrace Mons and Pavonis Mons, points to regional stretching of Mars's crust. Olympus Mons stands out due to its size and duration of volcanic activity, making it key to understanding Martian geology. Its study helps refine models of planetary volcanism, heat flow, and crustal stress. offering insights applicable to other planets like Venus and Mercury. The snowman Arrokoth, a trans-Neptunian object in the Kuiper Belt, was visited by NASA's New Horizons spacecraft in 2019. Arrokoth is a contact binary with two lobes that gently merged, preserving the early solar system's conditions. Its smooth, lightly cratered surface shows little geological activity, indicating it has remained largely unchanged for billions of years. Measuring about 36 kilometers in length, Arrokoth provides valuable evidence about how planetesimals, the building blocks of planets, formed in the early solar system. The gentle nature of its merger supports the theory that small bodies in the solar system merged under gravity rather than through violent collisions. Arrokoth, a contact binary in the Kuiper Belt, shows how planetesimals grew in stable, quiet regions of the solar nebula, rather than through violent impacts. Spectral analysis revealed organic molecules called tholins, which form when UV light interacts with ices like methane. These compounds are considered prebiotic and offer insight into the chemical processes that could have led to life in the solar system. Unlike comets, which experience heating and outgassing, Arrokoth has remained inactive in a stable orbit, with surface temperatures around -230 degrees Celsius. This inactivity allows researchers to study an ancient object in its original form, providing clues about early solar system conditions. Arrokoth's shape and surface uniformity suggest it formed slowly in a calm region of the solar system. This challenges earlier models that suggested chaotic collisions. If violent impacts had been common in the Kuiper Belt, objects like Arrokoth wouldn't have survived in such a pristine state. Its smooth surface and gentle merger of its lobes suggest that small bodies gradually combined under mutual gravity, not through high-speed impacts. This discovery influences our understanding of planetesimal formation, not just in our solar system, but also in other star systems. Uranus is unique in the solar system due to its extreme axial tilt of 98 degrees. This means the planet essentially rolls along its orbit, with one pole facing the sun for decades. The tilt likely resulted from a massive collision early in the planet's history. This collision may also explain some of Uranus's peculiar satellite system and internal structure. Uranus's magnetosphere is tilted and wobbles, creating complex magnetic fields that interact with the solar wind in unique ways. Despite the tilt, Uranus's atmosphere has a surprisingly uniform temperature, which suggests efficient atmospheric mixing. Uranus emits very little heat, making it one of the coldest planets in the solar system, despite receiving moderate sunlight. The planet's tilted rings and moons show that they likely formed in the same tilted plane after the hypothesized collision. The Voyager 2 spacecraft's flyby in 1986 provided the most detailed data on Uranus to date, offering insights into its atmosphere and magnetic field. Researchers are still studying Uranus's changing seasons and cloud activity, as its axial tilt complicates understanding of its weather patterns. Triton, Neptune's largest moon, is one of the most geologically active bodies in the outer solar system. Unlike typical volcanic activity, Triton has cryovolcanism, eruptions of volatile substances like water, ammonia, or nitrogen, which act like lava in extreme cold. These eruptions shape Triton's surface, leaving dark streaks and indicating recent or ongoing activity. Voyager 2's 1989 flyby revealed plumes of dark material erupting from Triton, suggesting active cryovolcanism rather than just impact activity. Triton's retrograde orbit suggests it was captured by Neptune rather than formed in place. This capture likely caused tidal flexing, generating heat in its interior and leading to cryovolcanic eruptions. Despite a lack of significant tidal heating today, residual warmth may still exist beneath its icy surface, supporting the ongoing geological activity. Triton's surface is covered in nitrogen ice, and when sunlight warms darker material underneath, pressure builds and leads to explosive eruptions. This phenomenon is a rare example of solar heating triggering activity on a frozen moon. Triton's nitrogen greenhouse effect is a fascinating process. Thin nitrogen ice on its surface acts like a lens, focusing sunlight onto the underlying material. This raises the temperature enough for nitrogen to sublimate, creating pressure that causes eruptions, forming tall dark plumes. The surface shows signs of cryovolcanism, including calderas, smooth plains, and flow channels, resembling lava flows on Earth, but made of icy mixtures. These features suggest that Triton may still be geologically active, or was until recently. Triton's retrograde orbit indicates it was likely captured by Neptune from the Kuiper Belt. This capture would have caused tidal friction, heating Triton's interior and creating subsurface reservoirs, which may still fuel occasional eruptions. Triton shares similarities with Pluto, suggesting both originated as icy planetesimals. Spectroscopic studies confirm the presence of nitrogen, methane, and carbon monoxide ices on its surface. These ices are sensitive to temperature changes, and seasonal variations in sunlight may trigger activity, linking Triton's orbital position to its cryovolcanic eruptions. The nitrogen atmosphere on Triton likely results from the cycling of volatile materials between the surface and subsurface. This cryovolcanism provides important insights into how internal activity can persist far from the Sun. Similar processes may occur on moons like Enceladus and Europa, where subsurface oceans drive dynamic activity. Triton helps refine models of cryovolcanism under extreme conditions and demonstrates that small bodies can maintain geological activity through non-traditional heat sources. The solar system shows a striking pattern: rocky planets near the Sun and gas giants farther out. This arrangement is the result of temperature differences in the early solar system. Near the Sun, only rocky materials could form, while farther out, lower temperatures allowed ices to solidify, aiding the formation of gas giants. The gas giants formed quickly, capturing thick atmospheres before the solar nebula dissipated. In contrast, terrestrial planets like Earth grew through collisions and mergers of rocky planetesimals. The asteroid belt between Mars and Jupiter marks the transition between rocky and gas giants. It contains bodies that never formed into a planet due to Jupiter's gravitational influence. Some asteroids contain water ice, suggesting that the snow line may have crossed this region during the Sun's early evolution. The asteroid belt reflects the complex chemistry of the mid-solar system and provides evidence of material mixing. Models suggest that the gas giants may have migrated inward and outward during the early solar system. This migration reshuffled material and influenced the distribution of smaller bodies, helping explain why Jupiter didn't prevent terrestrial planets from forming. It also influenced the Kuiper Belt, a region beyond Neptune filled with icy objects like Pluto. These objects preserve primitive materials from the early solar system. The gas giants' gravitational influence shields the inner planets from comets and asteroids, while also destabilizing smaller bodies, sending material inward. This arrangement of planets creates structures like mean motion resonances, governing the orbits of minor bodies. This predictable system also appears in exoplanetary systems, with variations in the positions and sizes of gas giants. Studying these systems helps refine our understanding of planet formation and migration. Venus, despite being farther from the Sun than Mercury, is the hottest planet in the solar system. This is due to its thick atmosphere, which traps heat through an extreme greenhouse effect. Venus's atmosphere, composed mainly of carbon dioxide and sulfuric acid clouds, absorbs and re-emits infrared radiation, creating temperatures high enough to melt lead. This intense greenhouse effect causes Venus to have much higher temperatures than Mercury, even though it receives less solar radiation. Venus has a thick CO2 atmosphere, over 90 times Earth's pressure, creating a thermal blanket that traps heat. In contrast, Mercury has almost no atmosphere, with extreme temperature shifts from over 430 degrees Celsius during the day to minus 180 degrees Celsius at night. Venus's atmosphere ensures stable temperatures across the planet, day or night, due to its greenhouse gases. Its clouds, made of sulfuric acid, reflect sunlight but also trap infrared radiation, contributing to a runaway greenhouse effect. This was likely triggered by water evaporation, which amplified warming, leading to the loss of water and unchecked CO2 accumulation. Venus rotates slowly in the opposite direction of most planets, with a day lasting 243 Earth days. However, its atmosphere circulates faster, spreading heat and maintaining temperature uniformity. Winds in the upper atmosphere reach speeds of 300 km per h, helping distribute heat. The surface has volcanic plains and deformed crust from past volcanic activity, possibly linked to CO2 and sulfur releases. Soviet missions in the 1970s and 80s revealed rocky terrain, with extreme conditions that destroy landers quickly. Future missions will use aerial platforms or orbiters to study the atmosphere in more detail. An internet claim suggests the Giza pyramids align with Mars's Tharsis volcanoes, particularly Olympus Mons. While the arrangement may look similar, it's a coincidence. The pyramids were built by Egyptians based on cultural, religious, and topographic factors, not cosmic alignment. On the other hand, the Tharsis volcanoes were formed by volcanic processes on Mars and have no connection to human architecture. The pyramids span about 1 kilometer, while the Tharsis volcanoes stretch over 1,500 kilometers. Any similarities in shape are visual, not physical or intentional. Mars and Earth have different geophysical conditions, including axial tilt and rotational periods, making any connection between these features purely speculative. This kind of pattern recognition, where we see meaning in unrelated things, often misleads public understanding of science. Real scientific analysis ignores superficial similarities and focuses on rigorous data and evidence. Cold welding occurs when two clean metal surfaces bond in space without heat. As there's no atmosphere to prevent it, metals can fuse at the atomic level when pressed together in a vacuum, forming a permanent bond. On Earth, oxidation or gas layers prevent this from happening. This phenomenon was discovered during early space missions. Metals like aluminum, copper, and gold are more prone to cold welding, especially when clean. Spacecraft engineers account for it by using different materials or coatings to prevent unwanted bonding at contact points. Cold welding could have potential uses for space manufacturing or repairs, where components can be bonded in orbit without traditional welding methods. Cold welding occurs when two clean metal surfaces come into contact in space, allowing atoms to migrate and bond at the atomic level. This results in a strong joint, as strong as the material itself, if the surfaces are clean and aligned correctly. On Earth, cold welding is rare due to air and contaminants, but it can be replicated in vacuum chambers for research, especially in nanotechnology and microelectromechanical systems, MEMS. Early metalworking might have unknowingly involved cold welding, as ancient smiths hammered clean metal surfaces together. This process offers insight into atomic bonding and material behavior in space. Engineers now account for it when designing space hardware to prevent unwanted bonding. ETHA's Euclid Space Telescope recently revealed 26 million galaxies in just 1 week, covering only 0.4% of its planned sky survey. It uses a visible imager near-infrared spectrometer to map galaxy shapes and red shifts. Euclid's early findings include over 380,000 galaxies and nearly 500 gravitational lens candidates. The telescope aims to survey over a third of the sky and study dark energy and cosmic expansion. Euclid's combination of AI and citizen science accelerated the cataloging process, promising to revolutionize our understanding of the universe. Jupiter emits twice as much energy as it receives from the Sun, thanks to internal heat. This excess heat is due to its massive size, formation history, and gravitational contraction. Helium rain in Jupiter's atmosphere could also contribute to its internal heat. This thermal energy drives complex weather systems, including powerful jet streams and the Great Red Spot. Jupiter's heat also affects its moons like Europa and Io, influencing their temperature balance. While Saturn also emits more heat than it receives, Jupiter's internal heat plays a more significant role in its dynamic weather. Earth has more trees than the Milky Way has stars. There are about 3 trillion trees on Earth, while the Milky Way contains between 100 to 400 billion stars. This surprising comparison shows the vast scale of life on our planet and highlights the importance of forests in maintaining global biodiversity. Counting stars in the Milky Way is done indirectly since most stars are too far or faint to observe directly. Astronomers use models and infrared surveys to estimate their numbers, which range from 100 to 400 billion. This uncertainty arises from factors like the number of low-mass stars and interstellar dust. Despite these challenges, the number of stars is still smaller than Earth's tree population. This highlights Earth's biosphere's productivity, where each tree plays a role in carbon, water, and energy cycles. Trees help regulate climate, store carbon, and support biodiversity through photosynthesis, which is unique to Earth. While stars are much larger and longer lived than trees, trees have a vital role in maintaining habitable conditions on Earth. A single star may live for billions of years, but trees help sustain life on our planet. The vast number of trees also contributes to Earth's resilience against atmospheric changes. This comparison shows how life on Earth is densely packed compared to the cosmos. However, human activity has reduced the number of trees by nearly 50% since the start of agriculture, making the current tree population even more significant. Saturn's North Pole features a stable hexagonal cloud pattern, observed since the 1980s. Is hexagon, formed by fast-moving winds at about 320 km per h, spans 30,000 km across, more than twice Earth's diameter. It is not a solid structure but a dynamic jet stream. The hexagonal shape is created by a planetary wave, which forms due to the planet's rotation and pressure variations. This structure is long-lived, rotating with Saturn, but at a different rate than the planet's interior. Infrared imaging shows the hexagon exists at various atmospheric levels. While visible during Saturn's spring and summer, it fades during winter but remains visible in infrared wavelengths. A large polar vortex sits at the center, surrounded by the hexagonal jet stream. Seasonal shifts in color from blue to gold occur due to chemical reactions in the atmosphere, further highlighting Saturn's dynamic atmosphere. The Big Ring is a massive cosmic structure composed of galaxies and clusters spanning 1.3 billion light-years. Discovered through statistical analysis, this formation challenges the traditional view that the universe is homogeneous on large scales. The discovery of such a large structure forces scientists to reconsider the assumptions in cosmological models. The Big Ring's size, extending beyond previously defined boundaries, suggests that the universe may have larger structures than thought. It could result from projection effects, gravitational interactions, or fluctuations in early universe density. Other large-scale structures like the Sloan and Great Wall have pushed the limits of our understanding, and the Big Ring further complicates the picture of the universe's matter distribution. These ideas remain speculative and require further data and simulations to support them. One challenge in confirming the Big Ring's nature lies in observation limits. Redshift distortions, incomplete data, and projection effects can create patterns that appear coherent but may be statistical flukes. Cross-verifying with independent surveys across multiple wavelengths is necessary to distinguish genuine features from observational artifacts. If the Big Ring is confirmed, it could point to anisotropies in the early matter distribution or unaccounted for physics in the inflationary era. Such deviations might affect how we model the cosmic microwave background, gravitational lensing, and the universe's expansion history. Europa and Io experience extreme tidal forces due to their elliptical orbits and interactions with Jupiter and other moons. This tidal heating generates enough internal friction to maintain liquid oceans beneath their surfaces. Europa's subsurface ocean, protected by tidal flexing, would freeze without this internal heat. Europa's orbital resonance with Io and Ganymede keeps its orbit slightly elliptical, maintaining tidal forces that continuously deform and heat the Moon. Europa's surface shows signs of these interactions, such as ridges and cracks. Its tidal heating also sustains the ocean and may allow nutrient mixing, which is important for potential habitability. Io experiences even more intense tidal heating, making it the most volcanically active body in the solar system. This activity is driven by tidal forces that melt its interior, creating lava reservoirs and erupting volcanoes. Unlike Europa, Io does not have a subsurface ocean, but instead undergoes silicate volcanism. Tidal heating on both moons creates stable environments, even at distances from the Sun where solar energy isn't enough to maintain liquid water. Europa's liquid ocean and rocky seafloor, combined with possible hydrothermal activity, make it a target in the search for extraterrestrial life. Missions like NASA's Europa Clipper and ESA's JUICE will investigate its subsurface and magnetic environment to better understand the conditions for habitability. Earth is constantly bombarded by meteoroids, ranging in size from dust grains to small boulders. These meteoroids come from asteroids, comets, and other debris and enter Earth's atmosphere at speeds of 11 to 72 kilometers per second. Most burn up due to friction with the atmosphere, creating bright streaks of light known as meteoroids. Only a small fraction survives as meteorites. The majority of incoming particles are small, but they add up to several tons of dust that settles on Earth's surface each day. This material provides information about the solar system's formation and composition. Larger meteoroids capable of producing fireballs are rare but can create significant impacts. Events like the Chelyabinsk explosion in 2013 remind us of the risks posed by larger objects. Earth's atmosphere acts as a shield, incinerating most meteoroids before they cause harm. Meteorites contain elements like sodium and iron, which contribute to atmospheric chemistry. Studying meteoroid interactions with the atmosphere provides insights into planetary science and defense. Meteor showers, like the Perseids or Geminids, occur when Earth passes through streams of debris. These events offer opportunities to study meteoroid dynamics and material properties. Radar and optical networks track meteors and fireballs, refining models of meteoroid flux and impact risks. They also guide recovery efforts for meteorites, which offer pristine samples from early solar system bodies. In addition to natural meteoroids, human-made objects like defunct satellites also re-enter Earth's atmosphere. Most burn up, but some fragments survive. Analyzing the trajectory and spectral signatures helps distinguish between natural and artificial entries. Meteorites, such as the Taish Lake meteorite, contain water-bearing minerals and organic compounds, providing clues about water-rich materials beyond Earth. The Taish Lake meteorite, discovered in Canada in 2000, contains up to 20% carbon-rich material and shows signs of aqueous alteration, confirming that its parent asteroid once harbored liquid water. These findings support the idea that water and organic molecules may have been delivered to early Earth through asteroid and meteorite impacts. In the early solar system, collisions between planetesimals and Earth were common. Primitive bodies, like those that created the Taish Lake meteorite, might have been the primary carriers of volatile compounds, bringing water and prebiotic chemistry to our planet. Isotopic analysis of hydrogen in meteorites strengthens this theory, as the ratio of deuterium to hydrogen in some meteorites closely matches that of Earth's oceans. This suggests a shared source or similar conditions for formation. While comets were once thought to be the main source of Earth's water, their isotopic signatures differ from Earth's, making water-rich asteroids a more likely source. Meteorites such as Murchison and Arail also contain hydrated minerals and organic compounds, originating from the outer asteroid belt. Their unaltered composition reflects the early solar system's chemical environment. The survival of water and organics in these meteorites depends on their entry conditions, as many meteoroids vaporize in the atmosphere. Slow entries or larger parent bodies allow fragments to reach the ground intact, especially when recovered quickly in cold environments like Antarctica. This delivery of water through asteroid impacts could explain how Earth became habitable. The presence of water on Mars, Ceres, and some moons suggests this process occurred across the solar system. Studying meteorites like Taish Lake can help scientists understand planet formation throughout the galaxy. Jupiter and Saturn's migration reshaped the solar system, significantly altering its architecture. The Grand TAC model proposes that Jupiter initially moved inward toward the Sun, then reversed direction due to gravitational interactions with Saturn. This migration scattered gas and dust, explaining why Mars is smaller than Earth and Venus. As Saturn migrated inward, it caught up with Jupiter, creating a 3-2 orbital resonance, and causing both planets to move outward. This movement redistributed material in the outer solar system, influencing the asteroid belt and the ice giants' formation zones. The Grand TAC model helps explain the asteroid belt's composition, containing both rocky and icy bodies. Simulations show that without Jupiter's inward movement, there would be too much mass near Mars's orbit. The Grand TAC provides a natural mechanism for the observed planetary sizes and positions. This migration process is tied to the presence of a protoplanetary gas disk, which existed in the early solar system. Such migrations are common in exoplanet systems, lending credibility to the model. The Grand TAC fits into a larger narrative of planetary evolution, with a nice model describing later instability among the outer planets. Together, these models explain how gravitational interactions shaped the current orbits of planets and small bodies. Evidence from meteorites and Kuiper Belt objects further supports planetary migration. The Grand Tack is a critical framework for understanding how massive planets reshape planetary systems, suggesting that Jupiter and Saturn migrated before settling into their current positions.